Something is pulling us. Right now, as you sit still, as you breathe, as you believe yourself to be motionless, you are being dragged through space at 600 kilometers per second toward a destination you cannot see. Not just you, not just Earth, not just the Sun or the solar system. 100,000 galaxies, including our own, are caught in a cosmic current so powerful it overrides the expansion of the universe itself. And we are moving towards something we have never been able to look at directly. For decades, astronomers called it the Great Attractor, a gravitational anomaly 250 million light-years away, hidden behind the densest part of our own galaxy, sitting in a region so obscured by dust and stars that we named it the Zone of Avoidance. It is not a black hole, it is not a single object, it is something far stranger. A region of space with the mass of tens of thousands of galaxies, pulling everything within hundreds of millions of light-years toward a center we still cannot fully map. The motion was discovered in the 1970s when scientists noticed galaxies were not behaving the way they should. They were drifting, all of them, in the same direction, as if responding to a hand we could not see. By 1986, they had traced the pull back to a single zone in the sky. But when they pointed their telescopes there, they found almost nothing. Just the faint glow of distant clusters buried beneath the light of our own stars. So how does something invisible move 100,000 galaxies? How fast are we really going? And what happens when you realize that after 10 billion years of drifting, we will never actually arrive? This is that story. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. The Milky Way galaxy is falling. Right now, this moment, as you sit still and breathe and imagine yourself planted on solid ground, you are being pulled through space at 600 kilometers per second towards something you cannot see, not drifting, not coasting on the expansion of the universe. Falling, in the way a stone falls toward the Earth, drawn by a force so large and so patient that the trip will take hundreds of millions of years to complete. You will never arrive. Your children's children, millions of generations down, will never arrive. But the fall is real, the pull is measurable, and for decades after we first detected it, we had absolutely no idea what was doing the pulling. This is the story of the Great Attractor. Not a black hole, not a star, not a planet or a nebula or any single object you could point a telescope at and call by name. It is a place, a region, a zone of space roughly 150 to 250 million light-years away, where gravity has piled up in ways that defy the simplest models of how the universe should behave. And it is dragging us, along with roughly 100,000 other galaxies, toward a point we still cannot fully see. The discovery did not come from a telescope, it came from math. In the 1970s and early 1980s, astronomers were doing something that sounds straightforward but is maddeningly difficult in practice. They were trying to measure how fast galaxies were moving. Not just away from us, which had been understood since Edwin Hubble's work in the 1920s, but in 3 dimensions, sideways, up, down, the full vector. Because the universe is expanding, every distant galaxy should be receding from us at a speed proportional to its distance. Double the distance, double the speed. That relationship is clean, predictable, encoded in what we call the Hubble flow. It is the baseline hum of cosmic expansion, the thing everything should be doing if gravity were spread perfectly evenly across space and nothing unusual were happening. Except that is not what the measurements showed. Galaxies in our local neighborhood were moving faster than the Hubble flow predicted, and they were not moving randomly. They were moving together, as if caught in a current. The technical term for this deviation is peculiar velocity, which is one of the great understatements in astronomical jargon. There is nothing peculiar about it in the sense of quirky or odd. It is peculiar in the older meaning of the word, particular to the object, specific, local. A galaxy's peculiar velocity is the component of its motion that has nothing to do with cosmic expansion and everything to do with gravity tugging it off course. When you measure a galaxy's redshift, you are reading how much its light has been stretched by the expansion of space as it traveled toward you. That tells you how fast it is receding along your line of sight. But if the galaxy also has a peculiar velocity, if it is being pulled sideways or toward you by the gravity of nearby mass, that motion adds to or subtracts from the redshift. Untangling the two requires careful work. You need distances that do not rely on redshift alone, independent measurements using standard candles like supernovae or the brightnesses of certain types of stars. Then you compare the distance-based expectation to the actual observed redshift, and the difference is the peculiar velocity. By the early 1980s, astronomers had done this for enough galaxies to see a pattern, and the pattern was alarming. Galaxies across a volume of space hundreds of millions of light-years wide were all drifting in the same direction, not scattering outward evenly the way cosmic expansion should carry them. Flowing. The word that kept appearing in the literature was bulk flow, the collective motion of a huge ensemble of galaxies as if they were leaves floating on the surface of a river. Rivers flow because the ground beneath them slopes. Galaxies flow because the distribution of mass around them is uneven. Somewhere out there, in the direction the flow was pointing, there had to be an enormous concentration of matter. More mass than a single galaxy cluster. More mass than anything that had been catalogued up to that point. And it was pulling everything in the local universe toward it, like water circling a drain. The problem was that no one could see it. The direction the galaxies were moving toward, the point in the sky where this invisible hand seemed to be located, sat behind the plane of the Milky Way. Picture the Milky Way as a flat disk of stars, gas, and dust stretching across the night sky. If you want to look out into the universe beyond our galaxy, the clearest views are perpendicular to that disk, straight up or straight down relative to the galactic plane. But if you try to look through the plane, you are staring through the thickest, dustiest, most crowded part of our own galaxy. Billions of stars, clouds of gas, lanes of dust that absorb and scatter light. Astronomers call this region the Zone of Avoidance, and for most of the 20th century it was effectively opaque. Anything sitting behind it was invisible to optical telescopes, hidden behind the clutter of our own cosmic neighborhood. So here was the situation in the mid-1980s. Something massive was out there, pulling on everything within a sphere hundreds of millions of light-years across. The math was solid. The peculiar velocities were real. The direction was known. And the object itself, or the region, or whatever it was, could not be observed. It was as if someone had calculated the orbit of an unseen planet by watching how it tugged on the objects around it. Except, in this case, the unseen planet weighed as much as tens of thousands of galaxies and was hiding behind a wall we could not see through. In 1986, a team of astronomers formally published the location. They called it the Great Attractor. The name stuck not because it was poetic, though it is, but because it was accurate. This was not a minor gravitational anomaly. This was not a slight deviation in a few galaxy orbits. This was a systematic, large-scale, undeniable pull affecting the entire local volume of the universe. The center of the attraction was calculated to lie roughly 150 million light-years away in the direction of the constellations Triangulum Australe and Norma, deep in the southern sky, squarely inside the zone of avoidance. The mass required to produce the observed velocities was estimated at around 10 to the 16th solar masses, that is 10,000 trillion times the mass of our Sun. Or if you prefer to think in galaxies, the equivalent of tens of thousands of Milky Ways piled into one region. The early estimates were rough. They had to be. You cannot weigh something you cannot see. What astronomers were doing was essentially forensic physics, reconstructing the shape and size of an object from the disturbances it left in its surroundings. Think of it like finding a massive footprint in the mud and trying to figure out what made it. You know something big walked through. You can measure the depth, estimate the weight, calculate how fast it was moving, but until you see the thing itself, you are guessing. And in this case, the footprint stretched across half the observable local universe. For a while, the Great Attractor was treated as the dominant feature in our cosmic neighborhood. The assumption was that this single, extraordinarily dense region was the primary driver of galaxy motions within a few 100 million light-years. Our Milky Way, the Andromeda Galaxy, the Virgo Cluster, the Hydra Centaurus Supercluster, all of it was falling toward this one point. The image that took hold in the popular imagination was of a hidden monster, a gravitational leviathan lurking in the dark, pulling galaxies toward it like a whirlpool pulling ships. That image was not entirely wrong, it was just incomplete. Because, as observations improved and the maps grew more detailed, it became clear that the Great Attractor was not alone. It was not some singular outlier, some freak concentration of mass that had no business existing. It was part of a larger structure, a web of galaxy clusters and superclusters interconnected by filaments of dark matter and separated by vast voids. The universe, it turns out, is not smooth. It is not a uniform soup of galaxies scattered evenly across space. It is a foam, a network, a cosmic web where matter clumps along invisible threads and galaxies collect at the intersections. The Great Attractor sits at one of those intersections, a major one, yes, a significant node in the web, but not the only one. By the 2000s, astronomers had begun to piece together a more complete picture. The Great Attractor was identified not as a single object, but as a region, a gravitational focal point within a much larger structure that eventually got a name of its own, Laniakea, Hawaiian for immeasurable heaven. Laniakea is a supercluster, a collection of galaxy clusters bound together by gravity and flowing toward a common center. That center is the Great Attractor. Laniakea contains roughly 100,000 galaxies spread across a volume of space about 520 million light-years in diameter. The Milky Way sits near the outer edge. We are not at the center. We are in the suburbs, drifting inward along with everything else. This reframing changed the nature of the mystery. The question was no longer what is the Great Attractor, as if it were a single hidden object waiting to be uncovered. The question became what is happening in that region that makes it the gravitational center of such an enormous volume of space. And the answer, as best as we can tell from the data we have now, is that the Great Attractor is not so much a thing as it is a place, a convergence point. The bottom of a gravitational well carved out by the combined mass of multiple galaxy clusters, all piled into a relatively small region of space, all pulling on each other and on everything around them. The most visible component of the Great Attractor, the piece we can actually point instruments at and study, is a massive galaxy cluster called the Norma cluster, also catalogued as Abell 3627. It sits almost exactly where the center of the Great Attractor was calculated to be, and it is huge, hundreds of galaxies bound together by gravity, surrounded by a halo of dark matter that outweighs the visible galaxies by a factor of 5 or more. But even Norma is not enough on its own to account for the full strength of the pull. There are other clusters nearby, other structures contributing to the mass. The region is crowded, dense, a pile-up of matter in a part of the universe that, from our vantage point, is maddeningly difficult to observe. And that is where things sit today. We know the Great Attractor exists. We can measure its effect on galaxy velocities. We have identified some of the structures responsible for its gravity. But we still cannot see the full picture because a significant portion of it is still hidden behind the plane of our own galaxy. Infrared telescopes and radio observations have helped. They can see through dust in ways optical telescopes cannot. X-ray observations have mapped the hot gas between galaxies in clusters like Norma, giving us a sense of the total mass. But there are limits. Large parts of the Zone of Avoidance remain poorly mapped, and we are left inferring the presence of mass from its gravitational signature rather than observing it directly. What makes the Great Attractor so unsettling is not that it is unusual, it is that it is not. The universe is full of superclusters. Laniakea is just one of many. There are larger structures, denser regions, more massive concentrations of galaxies elsewhere in the cosmos. The Great Attractor only feels special because it is close enough to affect us and hidden just well enough to have stayed mysterious for decades. It is a reminder that we live inside the thing we are trying to study, and our view is obstructed by our own position. We are trying to map the room from inside the room, and some of the walls are in the way. The discovery of the Great Attractor also forced a reckoning with scale. When Hubble first measured the expansion of the universe, the assumption was that on large enough scales, everything was moving away from everything else in a smooth, predictable way. Local gravity could pull galaxies together into clusters, sure. But once you zoomed out far enough, the expansion should dominate. The Great Attractor showed that large enough was bigger than anyone thought. Gravity was still in control across distances of hundreds of millions of light-years, shaping flows and currents that persisted across volumes of space containing 100,000 galaxies. The universe was not expanding uniformly. It was expanding in a lumpy, chaotic, richly structured way, and the lumps were enormous. So here we are, falling at 600 kilometers per second toward a point in space we still cannot fully see, part of a flow that has been underway for billions of years and will continue for billions more. The pull is gentle by human standards. You do not feel it. It does not register on any instrument in your daily life. But it is there, constant and inexorable, written into the motion of every star in the Milky Way and every galaxy in our local supercluster. We are passengers in a current we did not choose and cannot escape, drawn toward a place that for most of the history of astronomy was invisible. The Great Attractor is not a monster. It is not a threat. It is just gravity doing what gravity does, pulling matter together, shaping the universe one galaxy at a time. And the fact that it took us so long to even notice it was there tells you something about how much we still do not see. The Zone of Avoidance is still there, still blocking our view, still hiding whatever else might be waiting in the dark. And that is where the next part of the story begins. Standing in the way of one of the greatest discoveries in cosmology was something embarrassingly ordinary: our own galaxy. The Milky Way, home, the structure we live inside and have studied for centuries, turned out to be the single largest obstacle to understanding the mass distribution of the nearby universe. not because it is hostile or dangerous or inherently difficult to work around, but because it is in the way. Literally, physically, optically in the way. And for decades, that simple geometric fact turned one of the most massive structures in our corner of the cosmos into a ghost. The problem is dust, not the household kind you wipe off a table. Cosmic dust, tiny grains of carbon, silicon, and other elements forged inside dying stars and scattered into space when those stars exploded or shed their outer layers. Each grain is microscopic, smaller than the width of a human hair. Individually, they are harmless. Collectively, across the span of a galaxy, they are a wall. Dust absorbs and scatters light, particularly at shorter wavelengths like blue and ultraviolet. The more dust you look through, the dimmer and redder distant objects appear. Look through enough of it, and distant objects disappear entirely, swallowed by the haze. The Milky Way is a spiral galaxy, shaped like a flattened disk with a bulge in the middle and long arms curling outward. We sit inside that disk, about 2/3 of the way out from the center. From our vantage point, the disk appears as a band of light stretching across the night sky, the combined glow of billions of stars too far away to resolve individually. That band is beautiful. It has inspired myths and poetry in every culture that has looked up long enough to notice it. It is also packed with dust. The same spiral arms that contain the youngest, brightest stars also contain the densest clouds of gas and dust, the raw material from which new stars form. When you try to look through the plane of the Milky Way, you are staring through the longest possible path across that dusty disk. The result is an obscured strip of sky running all the way around the celestial sphere, roughly 20 degrees wide, where distant galaxies and extragalactic structures are either invisible or severely dimmed. Astronomers, in their gift for understatement, named this region the Zone of Avoidance. The name is older than you might think. It goes back at least to the early 20th century, when astronomers conducting the first large-scale surveys of galaxies began to notice a peculiar gap. Galaxies were scattered more or less evenly across most of the sky, but along the band where the Milky Way runs thickest, galaxy counts dropped off sharply. At first, this was not particularly mysterious. It was obvious that something was blocking the view. The assumption was that once better instruments came along, the problem would solve itself. Bigger telescopes, more sensitive photographic plates, longer exposures. Surely someone would find a way to see through the murk. Decades passed. Telescopes got bigger. Detectors got better. The Zone of Avoidance stayed opaque. By the time astronomers in the late 1970s were starting to piece together evidence of the Great Attractor, the Zone of Avoidance had become a known nuisance. But it was more than an inconvenience. It was a blind spot, and it sat directly between Earth and the region where the bulk flow of galaxies seemed to be heading. The math said there was something massive out there. The direction was clear. The observations necessary to confirm what that something actually was would require looking straight through the most obscured part of the sky. It was as if you were trying to watch a football game through a frosted window. You could hear the crowd, you could see shapes moving, but you could not make out the players or read the score. The frustration this caused in the astronomical community cannot be overstated. Understanding the large-scale structure of the universe, mapping where galaxies are and how they move, requires complete coverage of the sky. Miss a chunk and you miss potentially critical information about what is pulling on what, where the mass is concentrated, and how gravity is shaping the cosmic web. The Zone of Avoidance represented roughly 10% of the sky, maybe more depending on how conservatively you drew the boundaries. 10% does not sound like much until you realize that the structures you are trying to study, superclusters and galaxy filaments, can stretch across hundreds of millions of light years. A blind spot that size can easily hide an entire supercluster, which, as it turned out, is exactly what it was doing. For most of the 20th century, optical astronomy was the only game in town. You pointed a telescope at the sky, collected the light, recorded it on a photographic plate or later a digital detector, and analyzed what you saw. Dust was a problem optical astronomers learned to live with. You could correct for it to some extent if you knew how much dust was in the way, but that required auxiliary measurements and models, and in the thick of the zone of avoidance, the corrections became so large and so uncertain that the data was effectively unusable. Galaxies that would normally be bright enough to study became too faint to detect. The light that did make it through was reddened so severely that determining distances and velocities became guesswork. It was like trying to read a book through muddy water. Technically possible, but not worth the effort when there were clearer patches of sky to study instead. So for a long time, astronomers avoided the zone of avoidance. They worked around it. Surveys were designed to cover the parts of the sky where observations were reliable, and the obscured regions were left blank on the maps. This was not ideal, but it was pragmatic. If you cannot see something, you map what you can see and make a note of where the gaps are. The assumption, mostly unspoken, was that the hidden regions probably looked similar to the regions on either side of them. Galaxies distributed more or less evenly, nothing too surprising. That assumption, like many assumptions in astronomy, turned out to be wrong. The breakthrough came not from building bigger optical telescopes, but from looking at the sky in a different way. Infrared light, with its longer wavelengths, passes through dust much more easily than visible light. The same cloud of dust that completely blocks blue and green light will let infrared light through with only minor dimming. This has been understood in principle since the early 20th century, but building infrared telescopes sensitive enough to map faint galaxies was a challenge that took decades to solve. Infrared detectors had to be cooled to extremely low temperatures to avoid being blinded by their own heat. Observations had to be made from high-altitude sites or from space to avoid absorption by water vapor in Earth's atmosphere, which blocks much of the infrared spectrum. It was not until the 1980s and 1990s, with the development of space-based infrared observatories and ground-based telescopes equipped with advanced infrared cameras, that astronomers finally had the tools to peer through the zone of avoidance. The Infrared Astronomical Satellite, launched in 1983, was one of the first missions to systematically survey the entire sky in the infrared. Its primary goal was to detect cool objects like dust clouds, asteroids, and forming stars within our own galaxy, but it also picked up thousands of infrared bright galaxies beyond the Milky Way. Some of those galaxies sat in regions of the sky that were completely blank in optical surveys. For the first time, astronomers could see structure in the zone of avoidance. Not clearly, not with the kind of detail they were used to in other parts of the sky, but enough to confirm that there were galaxies there. A lot of galaxies. Follow-up observations using ground-based infrared telescopes in the 1990s began to reveal the outlines of galaxy clusters hiding behind the dust. The most significant of these was the Norma cluster, also catalogued as Abell 3627. Norma is massive, containing hundreds of galaxies and sitting almost exactly in the direction where the gravitational pull of the Great Attractor was calculated to point. Its discovery was not a surprise, exactly. Theorists had been predicting that something large had to be sitting in that region to account for the observed galaxy velocities, but confirmation mattered. Seeing the cluster directly, measuring its size and mass, and mapping its member galaxies turned the Great Attractor from an abstract mathematical inference into a physical object that could be studied. Infrared observations were only part of the solution. Radio astronomy also played a critical role. Neutral hydrogen, the most abundant element in the universe, emits radiation at a very specific wavelength of 21 centimeters, which falls in the radio part of the spectrum. That emission passes through dust without any trouble. Radio telescopes tuning into the 21 centimeter line could detect hydrogen in distant galaxies, even if the galaxies themselves were completely invisible in optical light. By measuring the Doppler shift of the hydrogen line, astronomers could determine the velocity of the galaxy, how fast it was moving toward or away from us. Combine that with enough measurements across the sky, and you could map the three-dimensional flow of galaxies, even in regions where you could not see the galaxies themselves. Surveys using this technique, particularly the H.I. Parkes All-Sky Survey, conducted in the late 1990s and early 2000s, filled in huge gaps in the zone of avoidance. Thousands of galaxies that had been hidden from optical view were detected for the first time. The maps that emerged showed not a smooth distribution of galaxies, but a continuation of the same large-scale structures, filaments and clusters and voids that were visible in the rest of the sky. The zone of avoidance was not empty, it was just hidden. And once you accounted for the dust and looked with the right tools, the structures behind it snapped into focus. X-ray astronomy added another layer. Galaxy clusters are not just collections of galaxies. They sit inside enormous halos of hot gas, heated to tens of millions of degrees by the gravitational energy released as the cluster formed. That hot gas emits X-rays, and X-rays, like infrared and radio waves, can pass through the dust in the Milky Way's disk. Space-based X-ray telescopes like the Roentgen satellite, launched in 1990, and later missions like Chandra and XMM Newton, mapped the X-ray glow of galaxy clusters across the entire sky, including the zone of avoidance. The X-ray data confirmed what infrared and radio observations had suggested. The region behind the Milky Way's disk was crowded with clusters, and the Norma cluster was one of the largest. None of these techniques individually gave a complete picture. Infrared observations could see the galaxies but struggled with precise distances. Radio observations gave velocities but missed galaxies with little neutral hydrogen. X-ray observations mapped the gas, but only in the most massive clusters. What finally cracked the problem was combining all three, along with optical data from the parts of the sky that were not obscured. By the early 2000s, astronomers had assembled a multi-wavelength atlas of the zone of avoidance, piecing together fragments of data from different parts of the spectrum into a coherent map. It was like restoring a torn photograph by overlaying copies taken with different filters. No single image was complete, but together they revealed the full picture. What that picture showed was not a single isolated mass concentration, but a complex, interconnected web of structures. The Norma cluster was there, yes, sitting near the calculated center of the Great Attractor. But it was not alone. Nearby were other clusters, other filaments of galaxies, all part of a larger concentration of matter that extended across tens of millions of light-years. The Great Attractor was not a point. It was a region, a gravitational basin carved out by the combined mass of multiple structures, all piled into a relatively small volume of space. The zone of avoidance had not been hiding a single monster. It had been hiding a neighborhood. The process of unveiling that neighborhood took more than 2 decades and required the cooperation of astronomers working across multiple wavelengths, multiple telescopes, and multiple continents. It was not a single eureka moment. It was a slow accumulation of data, each new observation filling in a little more of the map, each new technique pushing a little further into the obscured region. The zone of avoidance resisted. Even today, with all the tools modern astronomy has developed, parts of it remain poorly mapped. The dust is still there, the stars are still there, the obscuration is still real. But the mystery of what lies beyond has been largely solved, not by seeing through the dust in the way an optical astronomer would understand it, but by finding ways around the problem. Looking in wavelengths the dust does not block. Measuring properties of galaxies, velocity, hydrogen emission, X-ray glow, that do not require a clear optical view. Inferring the presence of mass from its gravitational effects, even when the mass itself cannot be seen directly. This workaround approach has become a template for solving similar problems elsewhere in astronomy. Anytime there is something you cannot observe directly, you find another way to measure it. Anytime there is a barrier, you look for a window. The zone of avoidance forced astronomers to develop those techniques, to think creatively about how to extract information from a sky that was not cooperating. In that sense, the obscured region was not just an obstacle, it was a challenge that drove innovation, a problem that demanded solutions. And the solutions that were developed, infrared surveys, radio mapping, multi-wavelength synthesis, have since been applied to questions far beyond the Great Attractor. There is a certain irony in the fact that one of the most significant structures in our local universe was hidden by the galaxy we live in. We are inside the thing blocking our view. We cannot step outside to get a clearer perspective. Every observation we make is filtered through the Milky Way's disk, colored by its dust, cluttered by its stars. The zone of avoidance is a permanent feature of our sky, a blind spot we will never fully eliminate. We can work around it, we can minimize its impact, but we cannot remove it. It is a reminder that our view of the universe is not objective. It is local, contingent, shaped by where we happen to sit and what happens to be in the way. The early astronomers who first mapped the distribution of galaxies and noticed the gap along the Milky Way's plane did not call it the zone of avoidance because they thought it was empty. They called it that because they could not see into it and chose to avoid the frustration of trying. For decades, that avoidance was a reasonable strategy. There were plenty of other parts of the sky to study, plenty of other galaxies to catalogue, plenty of other questions to answer. The obscured region could wait. But once the evidence for the Great Attractor started to pile up, avoidance was no longer an option. The most important structure in the local universe was sitting right behind the wall, and ignoring it was not going to make it go away. Astronomers had to confront the zone of avoidance directly, not because they wanted to, but because the universe had placed something too important to ignore exactly where it was hardest to see. That confrontation paid off. The structures revealed by infrared, radio, and X-ray observations in the 1990s and 2000s did more than solve the mystery of the Great Attractor. They filled in a missing piece of the cosmic map, a piece that connected structures on one side of the Milky Way's plane to structures on the other. Before those observations, the map of the local universe had a hole in it. Galaxy surveys on either side of the zone of avoidance showed clusters and filaments and voids, but it was not clear how they connected. Were they part of the same large-scale structures, or were they separate? Did the Milky Way sit at the edge of one supercluster or in the middle of a larger web? The zone of avoidance had made those questions impossible to answer. Once the dust was bypassed and the hidden galaxies were mapped, the connections became clear. The structures on either side of the obscured region were continuous. They were part of the same web. The Milky Way was not sitting at a boundary. It was embedded in the middle of a vast interconnected network of mass, and the Great Attractor was one of the densest nodes in that network. The story of the Zone of Avoidance is a story about limitations and how to work around them. It is about recognizing that the universe does not arrange itself for our convenience, and that sometimes the most important things are hidden in the least accessible places. It is about persistence, about building new tools when the old ones fail, about combining incomplete pieces of information into something that approaches completeness. And it is about accepting that some problems do not have perfect solutions. The Zone of Avoidance will always be harder to observe than the rest of the sky. The data will always be noisier, the maps less detailed, the uncertainties larger. But harder does not mean impossible. It just means you have to work for it. As the maps improved and the structures behind the Zone of Avoidance came into focus, the nature of the Great Attractor began to shift. It stopped being a mystery and started being a place, not a single object, but a region, not an isolated anomaly, but a node in a web. The gravitational pull that had first revealed its existence was real, but it was not coming from some unknown exotic source. It was ordinary gravity, the kind that holds galaxy clusters together and shapes the large-scale structure of the universe. The only thing unusual about it was the scale and the fact that it had taken so long to see the structures responsible. The Great Attractor was hiding in plain sight, obscured by our own galaxy, waiting for the right tools and the right perspective to reveal it. And once it was revealed, it became clear that it was not alone. The universe is full of such structures, massive concentrations of galaxies piled into dense regions, pulling on everything around them. The Great Attractor is just the one that happens to be close enough and massive enough to affect us. And now that we can see it, or at least see the structures that make it up, the next question is not what it is, but how it fits into the larger picture, how it connects to the rest of the cosmic web, where it sits in the hierarchy of structures that stretch across the universe from the smallest galaxy clusters to the largest superclusters and beyond. That is where the story goes next. The story so far has been about revealing what was hidden, about punching through the dust and building tools that could see what optical telescopes could not, about mapping the Zone of Avoidance and uncovering the structures that had been sitting behind it for billions of years. But revealing a structure is not the same as understanding it. Once you can see something, you have to figure out what it is, where it fits, and how it connects to everything else. And that is where the picture gets bigger, much bigger. The Great Attractor is not a freestanding object floating in empty space. It is part of a hierarchy, a nested set of structures that starts at the scale of individual galaxies and climbs upward through groups, clusters, superclusters, and eventually into the largest organization of matter the universe has to offer. Understanding the Great Attractor means understanding that hierarchy. You cannot explain why something is pulling on 100,000 galaxies without first explaining how 100,000 galaxies end up in the same neighborhood in the first place. Start small. A galaxy is a collection of stars, gas, dust, and dark matter bound together by gravity. The Milky Way is a galaxy, so is Andromeda, so are the hundreds of billions of other star systems scattered across the observable universe. Galaxies are not randomly distributed, they come in groups. The Milky Way, for example, is part of the local group, a collection of about 80 galaxies held together by their mutual gravitational pull. Most of those galaxies are small, faint dwarf galaxies that orbit the two dominant members, the Milky Way and Andromeda. The local group spans about 10 million light-years from edge to edge. By cosmic standards, that is a small neighborhood. Zoom out, and you find that groups of galaxies themselves are not isolated. They cluster. The local group sits near the edge of a much larger structure called the Virgo cluster, which contains more than 1,300 galaxies and spans roughly 15 million light-years. The Virgo cluster is massive enough that its gravity affects the motion of every galaxy within about 60 million light-years, including ours. We are not part of Virgo in the sense that we orbit within it, but we are close enough to feel its pull. The Milky Way and the rest of the local group are slowly drifting toward Virgo, drawn by the combined mass of all those galaxies piled into one region. Keep zooming out and you find that even clusters are not the top of the hierarchy. Clusters themselves group together into superclusters, vast assemblies of galaxy clusters connected by filaments of dark matter and separated by enormous voids where almost nothing exists. Superclusters are among the largest known structures in the universe. They stretch across hundreds of millions of light-years and contain thousands of galaxies, and the Great Attractor sits inside one of them. For decades, astronomers knew that galaxy clusters were clumped into larger structures, but mapping those structures was difficult. Galaxies in clusters are relatively easy to identify. They are densely packed, often visible in a single field of view, and their members are clearly associated with one another. Superclusters, by contrast, are sparse and sprawling. The galaxies within a supercluster are spread across such large volumes of space that recognizing the connections between them requires mapping not just where galaxies are, but how they are moving. That kind of map took time to build. It required measuring distances and velocities for thousands of galaxies across huge patches of sky, then analyzing the data to find patterns. By the late 20th century, those maps were starting to reveal something extraordinary. The universe is not smooth. It is not a featureless expanse with galaxies scattered evenly like grains of salt on a table. It is structured, organized into a pattern that looks less like a random distribution and more like a three-dimensional web. Astronomers call it the cosmic web, and it is one of the most striking features of the large-scale universe. Picture a spider's web stretched across a vast space, except instead of silk threads, the strands are made of dark matter, and galaxies collect along those strands like dewdrops on a web in the morning. Where the strands intersect, matter piles up into dense nodes. Those nodes are galaxy clusters and superclusters. Between the strands are voids, enormous regions of nearly empty space where galaxies are rare and the density of matter is far below average. The cosmic web is not a metaphor, it is a physical structure carved out by gravity over billions of years. In the early universe, matter was distributed almost uniformly, with only tiny variations in density from one region to another. Those variations, seeded during the first fractions of a second after the Big Bang, were the blueprint for everything that came later. Regions that were slightly denser than average had slightly stronger gravity, which pulled in more matter, which made them denser still. Over time, those overdense regions grew into the structures we see today. The densest regions became galaxy clusters. The underdense regions expanded into voids, and in between, matter flowed along invisible highways of dark matter, forming the filaments that connect the clusters. This process is called gravitational collapse, and it has been shaping the universe since the first few 100 million years after the Big Bang. Simulations of cosmic structure formation, run on some of the most powerful supercomputers in the world, reproduce the cosmic web with stunning accuracy. You start with a nearly uniform distribution of matter, add the rules of gravity and the expansion of the universe, and let the simulation run for billions of years. What emerges is a web of filaments and voids that looks almost identical to what we observe in the real universe. The agreement between simulation and observation is one of the great successes of modern cosmology. It tells us that we understand, at least in broad strokes, how the universe organizes itself on the largest scales. The Great Attractor is part of that web. It sits at one of the nodes, a place where multiple filaments converge and the density of matter is far above average. But identifying which node and how it connects to the surrounding web required more than just detecting a gravitational pull. It required mapping the distribution of galaxies in 3 dimensions across a volume of space large enough to see the web's structure. That work took decades, and it culminated in one of the most important discoveries in extragalactic astronomy, the identification of the supercluster that contains the Milky Way. For a long time, the Virgo cluster was assumed to be the gravitational center of our local region. The Milky Way and the local group were thought to be on the outskirts of a supercluster centered on Virgo, a structure sometimes called the local supercluster. That name suggested a cohesive, bound system with Virgo at the center and everything else, including us, orbiting around it. The problem was that the boundaries of the local supercluster were fuzzy. No one could agree on where it started or stopped, or whether it was even a meaningful structure. Were we part of Virgo's system, or were we part of something larger? The answer came in 2014 with the publication of a paper by Brent Tully and his collaborators. Tully, an astronomer at the University of Hawaii, had spent years compiling a database of galaxy distances and velocities, measuring the peculiar motions of thousands of galaxies in the local universe. Instead of assuming that galaxies were distributed into clusters and then asking how those clusters related to one another, Tully's team took a different approach. They mapped the flow of galaxies. Where are galaxies moving? What are they moving toward? By analyzing the velocity field, the team could identify regions where galaxies were flowing together, converging toward common centers of mass. Those convergence zones defined the boundaries of superclusters far more clearly than any static map of galaxy positions. What they found was that the Milky Way is not part of a supercluster centered on Virgo. It is part of a much larger structure, a supercluster that extends far beyond Virgo and includes the Great Attractor region. They called it Laniakea. The name, chosen by Tully's collaborator Naua Napoleon, comes from Hawaiian and translates to immense heaven or immeasurable heaven. The name fits. Laniakea is enormous. It spans roughly 520 million light-years from end to end and contains about 100,000 galaxies. The Milky Way sits near one edge, not at the center. Virgo, far from being the heart of our local universe, is just one of many clusters within Laniakea, and the gravitational center, the point toward which all the galaxies in Laniakea are flowing, is the Great Attractor. Laniakea is not a bound structure in the way a galaxy cluster is. Galaxy clusters are gravitationally bound, meaning the galaxies within them are held together by their mutual gravity and will remain together indefinitely. Laniakea is not bound. It is a region of convergent flow, a volume of space where galaxies are moving toward a common center, but that does not mean they will stay together. The expansion of the universe is still pulling space apart, and on the scales of superclusters, expansion eventually wins. Over time, the outer edges of Laniakea will drift away, carried off by the accelerating expansion driven by dark energy. Only the densest regions, like the Norma cluster and the other massive clusters near the center, will remain bound. The rest will disperse. This distinction is important. Laniakea is not a thing you can point to and say there it is. It is a pattern, a flow, a temporary configuration of matter shaped by gravity in a universe that is still expanding. The boundaries of Laniakea are defined by the regions where the flow changes direction, where galaxies stop moving toward the Great Attractor and start moving toward some other center of mass. Those boundaries are not walls. They are transition zones, places where the influence of one supercluster ends and the influence of another begins. And beyond Laniakea's boundaries are other superclusters, other nodes in the cosmic web, other regions where galaxies are flowing toward their own local centers of mass. The discovery of Laniakea changed the way astronomers think about the Great Attractor. Before 2014, the Great Attractor was often described as an isolated anomaly, a mysterious concentration of mass pulling on the local universe. After 2014, it became clear that the Great Attractor is not anomalous at all. It is the natural consequence of the cosmic web. Matter flows along filaments, accumulates at nodes, and those nodes become the gravitational centers of superclusters. The Great Attractor is simply the node at the center of Laniakea. It is large and massive, yes, but it is not unique. The universe is full of such nodes. We just happen to live close enough to this one for its gravity to affect us. The most prominent structure within the Great Attractor region is the Norma cluster, also catalogued as Abel 3627. Norma is a massive galaxy cluster containing hundreds of galaxies and sitting almost exactly where the gravitational center of the Great Attractor was calculated to be. It was one of the first structures detected in the Zone of Avoidance, revealed by infrared and X-ray observations in the 1990s. Norma is not small. It is one of the most massive clusters in the local universe, with a total mass, including dark matter, estimated at several times 10 to the 15th solar masses. That is thousands of times the mass of the Milky Way, concentrated into a region only a few million light-years across. Norma sits about 220 million light-years from Earth, making it one of the more distant major clusters in our local neighborhood. Its location, deep within the Zone of Avoidance, made it difficult to study for decades. Even today, large parts of the cluster remain poorly mapped because of the foreground dust and stars. But what has been observed confirms that Norma is a major player in the gravitational dynamics of the region. X-ray observations have mapped the hot gas surrounding the cluster, revealing a massive halo heated to tens of millions of degrees by the gravitational energy released as the cluster formed. Infrared surveys have catalogued hundreds of member galaxies, many of them large elliptical galaxies that have grown fat by cannibalizing their smaller neighbors. Radio observations have detected the neutral hydrogen in and around the cluster, tracing the flow of gas as it falls into the gravitational well. Norma is not the only cluster in the Great Attractor region. Nearby are several other massive clusters, including the Centaurus cluster and the Pavo-Indus supercluster. Together, these clusters form a dense concentration of mass that extends across tens of millions of light-years. The combined gravity of all these structures is what produces the pull we associate with the Great Attractor. It is not one object, it is a neighborhood. A pile-up of mass at a node in the cosmic web where multiple filaments intersect and galaxies have been flowing together for billions of years. The Norma cluster and its neighbors are not static. They are still growing, still accreting matter from the surrounding filaments, still merging with smaller groups of galaxies that wander too close. Galaxy clusters are the sites of some of the most violent events in the universe. When two clusters collide, the galaxies themselves usually pass through one another without directly colliding, because the distances between stars within galaxies are so vast. But the hot gas filling the space between galaxies does collide, and the result is a shock wave that heats the gas even further and sends X-rays blazing across millions of light-years. Observations of cluster collisions have provided some of the best evidence for the existence of dark matter, because the galaxies and the gas behave differently during a collision. The galaxies, which are mostly dark matter, sail through the collision largely unaffected. The gas, which is ordinary matter, slams into itself and gets left behind. Mapping the distribution of mass during a collision shows that most of the mass is in the galaxies, not the gas. That mass is dark matter. Norma and the other clusters in the Great Attractor region are likely the products of multiple such collisions over billions of years. They are the survivors, the structures that have grown large and massive enough to dominate their local environment. And their gravity is still shaping the flow of galaxies across hundreds of millions of light years. The hierarchy of structures in the universe is sometimes described as a ladder. Stars group into galaxies, galaxies group into clusters, clusters group into superclusters. Superclusters connect along filaments in the cosmic web. That description is accurate, but it can be misleading because it suggests a neat, orderly progression where each level is clearly defined and distinct from the one above and below it. The reality is messier. The boundaries between levels are blurry. Some galaxies are in clusters, others are not. Some clusters are part of superclusters, others are isolated, and superclusters themselves are not well-defined structures. They are patterns in the flow of matter, regions where galaxies are moving together, but those regions overlap and blend into one another in ways that make drawing sharp boundaries impossible. Laniakea, for example, is surrounded by other superclusters. To one side is the Perseus-Pisces supercluster. To another is the Shapley supercluster, one of the most massive concentrations of galaxies in the nearby universe. Shapley is so massive that some researchers believe it contributes as much to the motion of the Milky Way as the Great Attractor does. The boundary between Laniakea and Shapley is not a line you can draw on a map. It is a region where the flow shifts, where galaxies stop being pulled toward the Great Attractor and start being pulled toward Shapley instead. That transition happens gradually, not abruptly, and the exact location depends on how you define the flow. This blurriness is not a failure of the models, it is a reflection of how the universe actually works. Gravity does not care about boundaries or definitions. It acts everywhere, all the time, pulling on everything. The cosmic web is not a static structure. It is a dynamic, evolving pattern shaped by the competition between gravity, which pulls matter together, and the expansion of the universe, which pushes space apart. In regions where gravity wins, matter collapses into clusters and superclusters. In regions where expansion wins, voids grow and matter thins out. The boundary between those regimes is not sharp. It is a transition, a balance point. And that balance shifts over time as the universe expands and dark energy accelerates the expansion. The discovery of the cosmic web and the identification of Laniakea represent a major step forward in our understanding of the large-scale structure of the universe. For most of the 20th century, cosmology was focused on the universe as a whole. How old is it? How fast is it expanding? What is it made of? Those are critical questions, and answering them required looking at the universe on the largest possible scales, averaging over billions of light years to find general trends. But averaging obscures structure. It smooths out the lumps. The cosmic web is made of lumps, and understanding it requires zooming in, mapping the positions and motions of individual galaxies, and piecing together how those galaxies are organized into larger patterns. That work is still ongoing. Surveys like the Sloan Digital Sky Survey, the 2-degree Field Galaxy Redshift Survey, and more recent projects like the Dark Energy Survey and the upcoming Vera Rubin Observatory have been mapping the three-dimensional distribution of galaxies across larger and larger volumes of space. Each new survey reveals more of the web, more filaments, more voids, more clusters, and each new map refines our understanding of where we sit in that web. The Milky Way is not at the center of anything. We are in the suburbs of Laniakea, drifting toward the Great Attractor, along with 100,000 other galaxies, part of a flow that has been underway for billions of years and will continue for billions more. The structures we see today are not permanent. They are snapshots, moments in a process that has been running since the first stars ignited and will continue until the universe grows so diffuse that gravity can no longer pull anything together. The Great Attractor, Norma, Laniakea, all of it is temporary. On timescales of tens of billions of years, the expansion of the universe will tear these structures apart. The galaxies within Laniakea that are not gravitationally bound to the densest clusters will drift away, carried off by the accelerating expansion. The filaments will thin and break, the voids will grow. Eventually, the cosmic web will dissolve, leaving behind isolated clusters and groups of galaxies separated by unimaginable distances, too far apart to ever interact again. But that is far in the future. For now, the web is still here, still growing, still shaping the motion of galaxies across the universe. And the Great Attractor sits at one of its most prominent nodes, pulling on everything within reach, including us. Understanding that pull, understanding why we are moving toward it and how fast, and what will happen when we get there, requires understanding not just the Great Attractor itself, but the entire structure it is part of. The clusters, the superclusters, the filaments, the web. All of it fits together into a single interconnected system, a pattern of matter shaped by gravity and expansion over the entire history of the universe. The Great Attractor is not a mystery anymore. It is a place, a node in the cosmic web where matter has piled up and gravity has taken hold. The mystery now is not what it is, but how it connects to everything else. How the flow of galaxies through Laniakea links to the flows in neighboring superclusters. How the cosmic web formed in the first place, and how it will evolve in the future. Those are the questions that drive the field forward. And answering them requires continuing to map the universe, galaxy by galaxy, velocity by velocity, one piece of the web at a time. The map is not finished. It will never be finished. But every new piece brings us closer to understanding the structure we live in, the forces shaping it, and our place within it. That is the work. And the next step is to look more closely at the motion itself, at how galaxies move through the web, and what that motion tells us about the forces acting on them. The maps you saw in the last chapter, those three-dimensional reconstructions of the cosmic web, with their filaments and voids and clusters piled up at the intersections, were not built by pointing a telescope at the sky and taking a picture. You cannot photograph the large-scale structure of the universe the way you photograph a mountain range or a coastline. The universe does not pose for portraits. What astronomers did instead was something far more indirect, far more clever, and in some ways far more revealing. They measured motion, not the motion of stars or planets or asteroids, all of which are local, nearby, trivial in the grand scheme. They measured the motion of galaxies, thousands of them, tens of thousands. And from those measurements, they reconstructed not just where galaxies are, but where they are going, how fast they are moving, and what is pulling on them. That work, that vast project of measuring and mapping the flow of galaxies across hundreds of millions of light years, is how we know the Great Attractor exists. not because we saw it, because we felt its tug. The foundation of the whole enterprise is a relationship discovered nearly a century ago by Edwin Hubble. In the 1920s, working at the Mount Wilson Observatory in California, Hubble measured the distances to a series of galaxies using a technique involving a type of star called a Cepheid variable. Cepheids pulse in brightness at a rate that is directly tied to their true luminosity. Measure the pulse, calculate how bright the star actually is, compare that to how bright it looks from Earth, and you have a distance. It was tedious work, requiring long photographic exposures and painstaking analysis, but it worked. Hubble got distances to about 24 galaxies, far enough away that they were clearly outside the Milky Way, but close enough to measure with the instruments of the time. Then he did something else. He measured their velocities. That part was easier. When a galaxy is moving away from you, the light it emits gets stretched by the Doppler effect, the same phenomenon that makes an ambulance siren drop in pitch as it drives past. For light, the stretching shifts the wavelengths toward the red end of the spectrum, hence the term redshift. Measure the redshift of a galaxy's spectral lines, the fingerprints left by elements like hydrogen and calcium in its light, and you can calculate how fast it is receding. Hubble measured the redshifts of his galaxies, plotted them against their distances, and found something extraordinary. The farther away a galaxy was, the faster it was moving away. The relationship was linear. Double the distance, double the velocity, triple the distance, triple the velocity. This was not what anyone expected. If the universe were static, galaxies should be moving in random directions at random speeds, some toward us, some away, with no overall pattern. What Hubble found was a pattern so clear it practically screamed. Every galaxy he measured was receding, and the recession velocity increased with distance in a precise mathematical relationship. The only explanation that made sense was that space itself was expanding. The universe was not static. It was growing, stretching, carrying galaxies apart like dots drawn on the surface of an inflating balloon. The farther apart two dots are, the faster they move away from each other as the balloon expands. That was Hubble's law, and it revolutionized cosmology overnight. The relationship Hubble discovered is usually written as velocity equals Hubble constant times distance. The Hubble constant is just a number, a measure of how fast the universe is expanding. In practice, it tells you how much faster a galaxy recedes for every additional unit of distance you measure. The exact value of that constant has been argued over for decades, as we discussed earlier in the context of the Hubble tension, but the relationship itself is rock solid. The farther away a galaxy is, the faster it is moving away from us because of the expansion of the universe. This is the Hubble flow. It is the baseline, the expected behavior, the thing every galaxy should be doing if gravity were distributed perfectly evenly and nothing unusual were happening. Except gravity is not distributed evenly. The universe is lumpy. There are clusters, superclusters, filaments, voids. All that structure means that galaxies are not just being carried along by cosmic expansion. They are also being pulled by the gravity of nearby mass concentrations. A galaxy sitting near a massive cluster will be tugged toward that cluster, and that tug adds to or subtracts from the velocity caused by the Hubble flow. The result is a deviation, a difference between the velocity you would predict based on the galaxy's distance and the velocity you actually measure. Astronomers call this difference the peculiar velocity. The name is unfortunate because it makes the phenomenon sound rare or strange. It is neither. Every galaxy has a peculiar velocity. The Milky Way has one, Andromeda has one. The term peculiar in this context is not a judgment. It is a technical designation meaning specific to that object, local, not caused by the universal expansion. A galaxy's peculiar velocity is the component of its motion that has nothing to do with the stretching of space and everything to do with the gravitational influence of the structures around it. It is the part of the velocity that tells you what is pulling on the galaxy and how hard. Measuring peculiar velocities is harder than measuring redshifts. Redshift is straightforward. You take a spectrum, identify the spectral lines, measure how much they have shifted, and calculate the velocity. Done. But that velocity includes both the Hubble flow and the peculiar velocity mixed together. To separate the two, you need an independent measurement of the galaxy's distance, one that does not rely on its redshift. That way, you can calculate what the redshift should be based on Hubble's law, compare it to the actual redshift, and the difference gives you the peculiar velocity. Getting those independent distances is where the difficulty comes in. For nearby galaxies, you can use Cepheid variables, the same technique Hubble used. For more distant galaxies, Cepheids become too faint to see, and you have to move up the distance ladder to other methods. Supernovae, particularly Type Ia supernovae, are useful because they explode with a consistent peak brightness that can be calibrated and used as a standard candle. The Tully-Fisher relation, which links a galaxy's rotation speed to its intrinsic brightness, is another tool. There are others. Each method has its range, its uncertainties, its assumptions. Stringing them together into a coherent ladder that reaches hundreds of millions of light-years requires care, cross-checks, and a willingness to accept that your distance estimates will never be perfect. But they do not have to be perfect, they just have to be good enough to detect deviations from the Hubble flow. By the 1970s and 1980s, astronomers had accumulated enough distance measurements to start noticing something odd. Galaxies in a large region of the local universe were not moving the way Hubble's law predicted. Their peculiar velocities were not small random jitters. They were large, coherent, and pointing in the same direction. Galaxies across a volume of space, hundreds of millions of light-years wide, were all drifting together, as if they were caught in a current. This was not a handful of galaxies in a single cluster, all falling toward the center of the cluster. That would have been expected. This was thousands of galaxies spread across multiple clusters and superclusters, all moving in the same general direction with velocities of several hundred kilometers per second. The term that emerged to describe this phenomenon was bulk flow. A bulk flow is the average motion of a large sample of galaxies, the collective drift of an entire region. If galaxies were moving randomly, the bulk flow would average out to near zero. Some galaxies would be moving one way, others the opposite way, and the net motion of the ensemble would cancel out. But if the galaxies are being pulled by a large mass concentration, their peculiar velocities will be correlated. They will all be moving in roughly the same direction toward the source of the pull. The bulk flow will be large, persistent, and detectable even if individual galaxy velocities are noisy. The first clear evidence of a large-scale bulk flow came from surveys conducted in the 1980s. One of the most influential was the work of a group of astronomers who became known as the Seven Samurai, a nickname that stuck despite, or perhaps because of, its dramatic flair. The Seven Samurai measured distances and velocities for hundreds of elliptical galaxies, using the properties of their stellar populations as distance indicators. They found a strong, coherent flow extending across a region roughly 100 million light-years in diameter. The flow was pointing toward a region of the sky in the direction of the constellations Hydra and Centaurus, the same general direction where other teams had been detecting anomalies in galaxy motions. The implication was unavoidable. Something massive was sitting out there, pulling on everything within reach. The mapping of peculiar velocities accelerated through the 1990s and into the 2000s as surveys grew larger and techniques improved. One of the key advances was the development of multi-object spectrographs, instruments that could measure the redshifts of dozens or even hundreds of galaxies simultaneously. This made it practical to survey large volumes of space in a reasonable amount of time. Another advance was the use of infrared observations to identify galaxies in the zone of avoidance, filling in gaps in the maps that had previously been blank. Slowly, piece by piece, astronomers built up a three-dimensional picture not just of where galaxies are, but of how they are moving. The picture that emerged looked less like a static map and more like a weather chart. Imagine looking at a map of ocean currents. You see arrows pointing in different directions, showing the flow of water across the surface. The arrows are longer where the current is stronger, shorter where it is weaker. They converge in some places, diverge in others. You can trace the paths of the currents, see where they meet, see where they split. A map of peculiar velocities looks like that. Each galaxy gets an arrow showing the direction and speed of its motion relative to the Hubble flow. When you plot thousands of galaxies, the arrows form patterns, streams, flows, basins of attraction where the arrows all point inward, converging toward a common center. The Great Attractor showed up in those maps as a major convergence point. Galaxies across a huge region, stretching from the Virgo cluster on one side to the Centaurus and Hydra clusters on the other, all had peculiar velocities pointing in the same general direction, toward Norma, toward the Zone of Avoidance, toward the region where infrared and X-ray observations had revealed the Norma cluster and its neighbors. The flow was not uniform. Some galaxies were moving faster, others slower, depending on their distance from the center and the local gravitational environment. But the overall pattern was unmistakable. This was not random motion. This was a gravitational current, and it was pulling in everything within a few 100 million light-years. The strength of the flow told you something about the mass responsible. Newton's law of gravity is simple in principle. The force between two objects depends on their masses and the distance between them. More mass means more force. Less distance means more force. If you know how fast a galaxy is being pulled and how far away it is from the source of the pull, you can estimate the mass of that source. Do that for thousands of galaxies, and you can build up a detailed picture of the mass distribution across a huge volume of space. The peculiar velocities were saying that the Great Attractor region contained a staggering amount of mass, on the order of 10 to the 16th solar masses. Tens of thousands of galaxies worth of matter piled into a region a few tens of millions of light-years across. But here is where things got complicated. The more data that came in, the clearer it became that the Great Attractor was not a single isolated mass concentration. It was part of a larger structure, and there were other structures nearby contributing to the flow. The Shapley Supercluster, sitting about 650 million light-years away on the far side of the Great Attractor, is one of the most massive concentrations of galaxies in the local universe. Its gravity is strong enough to influence galaxy motions across hundreds of millions of light-years. Some studies suggested that the motion of the Milky Way and our local neighborhood toward the Great Attractor was partly driven by Shapley, pulling from beyond. The Great Attractor was not the end of the road. It was a way station, a step along a longer journey toward an even more massive structure. This realization led to a shift in how astronomers talked about the Great Attractor. Instead of treating it as a single object or a single destination, they started talking about it as a region, a focal point in a larger gravitational landscape. The motion of galaxies in the local universe was not being driven by one dominant mass. It was being shaped by the combined influence of multiple structures, all pulling and tugging on each other in a complex dance. The Great Attractor was the most prominent of those structures in our immediate neighborhood, but it was not acting alone. The culmination of this work came with the identification of Laniakea in 2014. Brent Tully and his team had spent years compiling a database of galaxy positions and peculiar velocities, carefully measuring distances using multiple independent methods and cross-checking their results. They did not start by assuming that the local universe was organized into superclusters and then trying to fit the data to that assumption. They started with the data and asked a simple question: where are the galaxies flowing? The answer defined the boundaries of Laniakea. Galaxies within Laniakea are flowing toward the Great Attractor. Galaxies outside Laniakea are flowing toward other centers of mass. The boundary between Laniakea and the neighboring superclusters is the line where the flow changes direction, where the gravitational influence of one structure ends and the influence of another begins. That boundary is not a wall, it is a watershed, the term Tully's team used to describe it. Think of water flowing down a mountainside. Depending on which side of the ridge you start on, the water flows into one valley or another. The ridge is the watershed, the dividing line between drainage basins. In the cosmic web, the watershed is the line between regions of space where galaxies are flowing toward different attractors. Laniakea's watershed marks the edge of the Great Attractor's influence. Cross that line and you are in the domain of a different structure, being pulled in a different direction. The maps that showed Laniakea also showed something else. The flow of galaxies is not smooth. It is turbulent, chaotic, full of eddies and vortices and regions where the currents clash. This is not because the physics is complicated, it is because the mass distribution is complicated. Every cluster, every supercluster, every filament of dark matter contributes to the gravitational field, and the field is constantly shifting as structures grow and merge and interact. The motion of an individual galaxy is the result of all those influences added together, weighted by distance and mass and geometry. The peculiar velocity field is a snapshot of that complexity, a freeze frame of a process that has been running for billions of years. Modern surveys have pushed the mapping of peculiar velocities to larger and larger scales. The Cosmic Flows project, led by Tully, has compiled distance and velocity measurements for more than 30,000 galaxies across a volume of space stretching several billion light-years in every direction. Other surveys have used different techniques. The 6DF Galaxy Survey measured redshifts for more than 100,000 galaxies in the southern sky, using statistical methods to infer the peculiar velocity field even when individual distance measurements were not available. The result is a set of maps that show the flow of galaxies not just in our local neighborhood, but across a significant fraction of the observable universe. Those maps reveal that the Great Attractor is not unique. The universe is full of such structures, massive concentrations of galaxies sitting at the nodes of the cosmic web, pulling on everything around them, shaping the flow of matter on the largest scales. The Great Attractor is special to us only because it is close enough to affect our motion and because it took so long to identify. From the perspective of a galaxy in another part of the universe, sitting near a different supercluster, there would be a different attractor, a different flow, a different set of structures dominating the local gravitational landscape. The physics is the same everywhere. The details depend on where you are. There is a certain beauty in this. The universe does not have a center. There is no privileged location, no special vantage point from which everything else is arranged. Every galaxy, every cluster, every observer sees a version of the universe organized around their own position. The Great Attractor is our local gravitational anchor, the structure that defines the motion of our corner of the cosmos. But it is not the center of the universe. It is just the center of our neighborhood. A neighborhood that happens to span 500 million light-years and contain 100,000 galaxies, but still, a neighborhood. The measurement of peculiar velocities is ongoing. Every new survey adds more galaxies, more data points, more detail to the maps. And with each new map, the picture of the cosmic web becomes sharper, the flows become clearer, the structures stand out in higher relief. We are still a long way from having a complete map of the universe. That may be impossible. The observable universe contains hundreds of billions of galaxies, and measuring the distance and velocity of each one individually is not practical. But we do not need complete coverage. We just need enough data to see the patterns, to identify the major structures, to trace the flows, and we have that. The maps we have today, built from decades of careful measurements and painstaking analysis, show a universe that is dynamic, structured, and shaped by gravity in ways that would have been unimaginable a century ago. The Great Attractor is the proof. Not because it is exotic or because it requires new physics to explain, but because it is there, sitting in the data, visible in the motion of thousands of galaxies, undeniable once you know how to look. It is a testament to the power of indirect observation, of using motion to infer the presence of mass, of building up a picture of the universe piece by piece from fragments of information. We cannot see the Great Attractor directly. Much of it is still hidden behind the Zone of Avoidance, but we can feel its pull, we can measure its effect, we can map the flow of galaxies toward it and reconstruct the gravitational landscape that produces that flow. And from that, we can understand not just what the Great Attractor is, but what it means. It means the universe is not static. It means structure matters. It means gravity is still shaping the cosmos on the largest scales, pulling galaxies together, carving out basins of attraction, driving flows that will continue for billions of years. The Milky Way is part of that flow. We are moving toward the Great Attractor at 600 kilometers per second, drawn by the combined gravity of tens of thousands of galaxies piled into one region of space. We are not alone in that motion. Every galaxy in Laniakea is moving the same way, caught in the same current, part of the same cosmic river. That motion connects us to the structures around us in a way that is both humbling and profound. We are not isolated. We are not drifting randomly through an empty void. We are part of a web, a network of matter and gravity that stretches across hundreds of millions of light years. The Great Attractor is the anchor point of that web, the center of the flow, the place where the currents converge. And understanding that flow, mapping it, measuring it, is how we know where we are. Not just in space, but in the structure of the universe itself. The next question is how you take all those measurements, all that data, all those velocity vectors, and translate them into something graspable. How do you make sense of the scale involved when the numbers climb into the hundreds of millions of light years and the masses reach tens of thousands of galaxies? That is where the story goes next. Numbers are supposed to mean something. When someone tells you a bridge is 2 kilometers long or a building is 400 meters tall, your brain has tools to process that information. You can picture it. You can compare it to things you know. A kilometer is about how far you can walk in 10 minutes. 400 meters is taller than most skyscrapers, but you have seen skyscrapers. The numbers connect to experience. They anchor themselves in reality. But when astronomers tell you that the Great Attractor lies roughly 250 million light-years away, those tools break. Your brain has nothing to grab onto. The number is too large. The units are unfamiliar. And the thing being measured, The distance to a region of space you cannot see and will never reach does not connect to anything in your daily life, so the number floats. It sounds impressive, it sounds big, but it does not mean anything. Not yet. Not until you work to make it mean something. Start with a light year. That is the distance light travels in 1 year. Light moves at about 300,000 kilometers per second. That is fast enough to circle the Earth 7.5 times in 1 second. Fast enough to reach the Moon in a little over a second. Fast enough that if you could somehow hitch a ride on a beam of light leaving the Sun, you would pass Earth in 8 minutes and reach the edge of the solar system, past Neptune and Pluto and the scattered disk of frozen debris at the outer edge, in about half a day. Keep going for a year at that same relentless speed and you will have traveled 1 light year, about 9.5 trillion kilometers, that is the unit. 1 light year, and the Great Attractor sits 250 million of them away. To put that in perspective, the nearest star to our Sun, Proxima Centauri, is about 2 light years away. If the Sun were a basketball sitting on a table in your living room, Proxima Centauri would be another basketball sitting roughly 6,000 kilometers away, somewhere in the middle of the Indian Ocean. The Milky Way galaxy, our home, spans about 100,000 light-years from edge to edge. If you shrank the Milky Way down so that 1 light-year equaled 1 centimeter, the whole galaxy would fit on a football field, 1 kilometer across. You could walk from one side to the other in about 10 minutes. The Andromeda Galaxy, our nearest large neighbor, sits about 2.5 million light-years away. On that same scale, where 1 light-year equals 1 centimeter, Andromeda would be 25 kilometers away. You could drive there in 20 minutes. Now take that scale and apply it to the Great Attractor, 250 million light-years. On the scale where 1 light-year equals 1 centimeter, the Great Attractor would be 2,500 kilometers away. That is the distance from New York to Los Angeles, from London to Cairo, from Tokyo to Bangkok. That is not a number you can wave away. That is a distance that means something. If you started walking at that scale, 1 centimeter per step, it would take you years to reach the Great Attractor, not months, years. And remember, every single one of those centimeters represents an actual light year, a distance so vast that light, the fastest thing in the universe, takes a full year to cross it. Scale it back up to reality, and the number becomes incomprehensible again. 250 million light-years is not a distance you can picture. It is not a distance you can feel. It is a number that exists only on paper, only in the abstract mathematics of cosmology, but it is real. The Great Attractor is out there, right now, at that distance, and its gravity is pulling on us. The region itself is not a point. It is not a single location you could mark on a map with a pin. The Great Attractor is a zone, a volume of space where mass has piled up and gravity has taken hold. Estimates for the size of that region vary depending on how you define its boundaries, but a reasonable figure is somewhere around 300 million light-years across. That is not the distance from here to there. That is the diameter of the region itself. Picture a sphere 300 million light-years wide, centered roughly 250 million light-years away in the direction of the constellations Norma and Triangulum Australe. That sphere contains the Norma cluster, the densest and most massive structure in the region, along with several other galaxy clusters and countless individual galaxies, all contributing to the total mass. It is not a uniform blob. The mass is clumped, concentrated in clusters, separated by filaments and voids. But taken together, the entire region acts as a single gravitational basin, pulling on everything within reach. The volume of space encompassed by that sphere is staggering. Volume scales with the cube of the diameter. Double the diameter and you multiply the volume by 8. Triple the diameter and you multiply the volume by 27. A sphere 300 million light-years across has a volume of roughly 14 million cubic megaparsecs. A megaparsec is about 3.26 million light-years. A unit astronomers use because light-years get cumbersome when you are talking about distances between galaxy clusters. 14 million cubic megaparsecs. That is the kind of number that makes your eyes glaze over because there is no intuitive way to grasp what it means. So try this instead. If you could fit one galaxy into every cubic volume the size of the local group, the collection of about 80 galaxies that includes the Milky Way and Andromeda, you could fit millions of such groups inside the Great Attractor region. Millions of neighborhoods, each one containing dozens of galaxies, all piled into one zone. That is the scale we are talking about. And the Great Attractor is not pulling on a handful of nearby galaxies. It is pulling on roughly 100,000 of them. That number comes from the definition of Laniakea, the supercluster that contains the Milky Way and extends across about 520 million light-years. Laniakea is not a bound structure. It is a region of convergent flow, a volume of space where galaxies are moving toward a common center. That center is the Great Attractor. Every one of those 100,000 galaxies, scattered across hundreds of millions of light-years, is drifting in the same general direction. Some are closer to the center, some farther away. Some are moving faster, others slower, depending on their position and the local gravitational environment. But all of them are part of the flow. All of them are falling. 100,000 galaxies is not a small number. The Milky Way contains somewhere between 200 billion and 400 billion stars. Call it 300 billion as a rough average. Multiply that by 100,000 and you get 30 quadrillion stars. That is 30 followed by 15 zeros. 30 quadrillion stars, all contained in galaxies that are all moving toward the same region of space. Not all of those stars are like our Sun. Many are smaller, cooler red dwarfs. Some are larger, hotter blue giants. Some are already dead, collapsed into white dwarfs, or neutron stars, or black holes. But they are all there, all part of the census, all caught in the same gravitational current. And every one of those stars is surrounded by space, vast, empty, silent space, stretching light-years in every direction before you reach the next star. Multiply that emptiness by 30 quadrillion, and you start to get a sense of the volume we are talking about. This is not a crowded region. It is not packed tight. It is mostly nothing. But the nothing is organized, it is structured, and it is moving. The idea that empty space can be part of a gravitational flow is not intuitive. We think of gravity as something that acts on objects. A planet pulls on a moon. A star pulls on a planet. A black hole pulls on anything that gets too close. But the space between those objects we imagine is neutral. It is just there, inert, a stage on which the action happens but not part of the action itself. That picture is wrong. Space is not separate from the things in it. Space is shaped by mass, curved by gravity, woven into the structure of the universe. When astronomers talk about the Great Attractor pulling on galaxies hundreds of millions of light-years away, they are not talking about some magical force reaching across the void. They are talking about the geometry of space itself, bent and warped by the mass concentrated in that region, creating a gradient that everything nearby slides down. The galaxies are not being pulled through space. They are following the shape of space, and that shape extends far beyond the visible boundaries of the mass creating it. Think of it this way. Drop a bowling ball onto a trampoline. The fabric dips, forming a depression around the ball. Roll a marble onto the trampoline and it will curve toward the bowling ball. Not because the ball is reaching out and grabbing it, but because the marble is following the slope of the fabric. The trampoline analogy is overused in physics education, and it has its limits. It suggests that gravity is caused by objects sitting on a surface, which is not quite right. But it captures something important. Mass warps space. That warping creates a gradient. Objects follow the gradient. The Great Attractor is the bowling ball. The 100,000 galaxies in Laniakea are the marbles. And the trampoline is space itself, stretched across hundreds of millions of light years, dipping and curving in response to the mass piled up in the center. The distance to the Great Attractor, that 250 million light years, is not just a measure of how far away it is also a measure of how long ago the light we see from that region was emitted. Light does not travel instantaneously. It moves at a finite speed, and over cosmic distances, that means there is always a delay between when something happens and when we see it. The light reaching our telescopes today from the Norma cluster, the most prominent structure in the Great Attractor region, left that cluster 250 million years ago. Back then, on Earth, the dinosaurs were in the middle of their reign. The continents were arranged differently. The climate was warmer. The Permian extinction, the most catastrophic loss of life in Earth's history, was still in the future. Humans obviously did not exist, would not exist for another 249 million years. And yet, at that moment, light was leaving the Norma cluster, beginning a journey that would last longer than the entire history of mammals on Earth. Every photon that completes that journey carries information about the cluster as it was back then. The stars that were shining, the galaxies that were colliding, the hot gas glowing between the clusters, all of it frozen in time, encoded in the light, traveling toward us at 300,000 kilometers per second. That delay matters because it means we are always looking at the past. The farther away something is, the further back in time we are seeing it. The Great Attractor, at 250 million light-years, is not far enough back to show us the early universe. 250 million years is recent by cosmic standards. The universe is nearly 14 billion years old. 250 million years ago, galaxies looked pretty much the way they do now. Stars were forming, living, dying, clusters were merging. The cosmic web was already in place. But the delay is still significant because it reminds us that the Great Attractor we are measuring, the region whose gravity we are mapping, is not the Great Attractor as it exists today. It is the Great Attractor as it existed 250 million years ago. The mass is still there. The gravity is still there, but the details have changed. Stars have been born and died. Galaxies have drifted closer or farther. The region has evolved, and we will not see that evolution for another 250 million years. The scale of the Great Attractor also forces a reckoning with the idea of neighborhood. We tend to think of the local universe as the space within a few tens of millions of light years. The local group, the Virgo cluster, may be the nearest galaxy clusters beyond that. That is local in the sense that it is relatively close enough that we can map individual galaxies in detail and measure their properties with reasonable precision. But the Great Attractor expands the definition of local to include structures hundreds of millions of light years away. Structures so far away that their light takes longer to reach us than complex life has existed on Earth. And yet, those structures are part of our neighborhood in a gravitational sense. They are close enough to affect our motion, close enough to shape the flow of galaxies across the entire region. Distance is relative. What counts as nearby depends on the scale of the forces you are considering. In terms of gravity, in terms of the cosmic web, the Great Attractor is local. It is part of our corner of the universe. It is the anchor point of the supercluster we live in, and that means 250 million light-years, as incomprehensibly large as that distance is still close enough to matter. Here is another way to think about the scale. The observable universe, the part of the universe we can see in principle, extends about 46 billion light-years in every direction. That is the radius, not the diameter. The full diameter is roughly 93 billion light-years. That size is larger than the age of the universe would suggest, because space itself has been expanding the whole time, stretching the light from distant objects and carrying them farther away. The Great Attractor at 250 million light-years sits well within that observable bubble. In fact, it is relatively close to us in the grand scheme. 250 million light-years is less than 1% of the radius of the observable universe. On a map of the cosmos, the Great Attractor would be practically next door, but that 1% still represents a distance so vast that human language struggles to convey it. A distance that light, traveling for 250 million years without pause, has only just now crossed. A distance that contains trillions of stars and billions of galaxies and incomprehensible volumes of empty space, all of it pulled into the same gravitational flow, all of it drifting toward the same unseen center. The number of galaxies involved, that 100,000 figure, is worth sitting with for a moment. Each one of those galaxies is a structure containing billions or hundreds of billions of stars. Each one has its own history, its own population of planets and gas clouds and dust and dark matter. Each one is a universe unto itself, complex and dynamic and full of things we will never catalogue or name. And each one is moving, not orbiting, not spinning in place. Moving through space, falling toward the Great Attractor at speeds of several hundred kilometers per second. That motion is slow by the standards of light, but fast by almost any other measure, 600 kilometers per second. The speed at which the Milky Way is drifting toward the Great Attractor is more than 2 million kilometers per hour. Fast enough to cross the distance from the Earth to the Moon in about 3 minutes. Fast enough to circle the Earth in 67 seconds. And that motion has been ongoing for billions of years. The Milky Way has been falling toward the Great Attractor since long before the Sun formed, long before Earth existed, long before anything you would recognize as life appeared in the universe. And it will keep falling for billions of years more, carried by a gravitational current that will not stop until the expansion of the universe tears the structure apart. The realization that most of the volume between here and the Great Attractor is empty is both comforting and deeply strange. Comforting because it means the space is not filled with obstacles. There is nothing in the way, no walls, no barriers, no regions of impassable density. Just galaxy after galaxy separated by vast gulfs of near vacuum, each one drifting along its own path through the web. Strange, because that emptiness is not passive, it is part of the structure. The voids between galaxies are not leftover scraps of space that happened to miss out when matter was being distributed. They are features of the cosmic web, regions where matter has been pulled away, drained into the filaments and clusters that surround them. The voids are shaped by gravity just as much as the clusters are. They are low-density regions sitting next to high-density regions, and the contrast between them is what defines the web. The Great Attractor sits at a node in that web, a place where filaments converge and matter has piled up. The space between us and the Great Attractor is not empty in the sense of being irrelevant. It is part of the gradient. It is the slope down which we are sliding. Scale is not just about distance, it is also about time. At 600 kilometers per second, how long will it take the Milky Way to reach the Great Attractor? The math is straightforward. 250 million light-years is about 4 times 10 to the power of 21 kilometers. Divide that by 600 kilometers per second and you get roughly 4 times 10 to the power of 18 seconds. Convert that to years and you get about 127 billion years. That is longer than the current age of the universe. The universe is 13.8 billion years old. We have been falling toward the Great Attractor for a significant fraction of that time, and we will keep falling for roughly 10 times longer than the universe has existed so far. Except we will not, because the universe is not static, it is expanding, and that expansion is accelerating. On timescales of tens of billions of years, the expansion will overcome the gravitational pull of the Great Attractor. The flow will reverse, the structure will dissolve. The galaxies within Laniakea that are not gravitationally bound to the densest clusters will drift apart, carried away by the expansion of space itself. The Great Attractor will not remain a gravitational anchor forever. It is a temporary structure, a pattern in the cosmic web that will eventually fade. But temporary does not mean insignificant. The Great Attractor has been shaping the motion of galaxies in this region for billions of years. It has been pulling matter together, driving flows, carving out the gravitational landscape that defines our corner of the universe. And it is still doing that right now. The 100,000 galaxies in Laniakea are still falling. The Milky Way is still drifting toward Norma at 600 kilometers per second. That motion connects us to the largest structures in the cosmos, to the web of filaments and voids and clusters that stretches across hundreds of millions of light-years. It reminds us that we are not isolated, we are not adrift in a featureless void. We are part of a system, a network, a flow, and that flow is shaped by the Great Attractor, by the mass piled up in a region of space so distant that its light takes longer to reach us than dinosaurs have been extinct, but close enough that its gravity still reaches across the gulf and pulls. The effort required to make 250 million light-years mean something, to translate it from an abstract number into a felt reality, is not trivial. It takes work. It takes analogies that stretch and break and have to be rebuilt. It takes sitting with the numbers, turning them over, comparing them to things you know until some fragment of understanding clicks into place. But that work is worth it because the scale is part of the story. The Great Attractor is not impressive just because it is massive or because it is pulling on us. It is impressive because of how far that pull reaches, because of how much space it encompasses, because of how many galaxies are caught in its current. The scale is the thing that turns the Great Attractor from a curiosity into something that rewrites your sense of what local means, what nearby means, what close enough to matter means. 250 million light-years, 100,000 galaxies, 30 quadrillion stars, hundreds of millions of cubic light-years of space, most of it empty, all of it organized into a flow that has been running for longer than Earth has existed. Those are the numbers, and behind the numbers is a structure, a region, a gravitational basin that sits at the center of our cosmic neighborhood and pulls everything toward it with a patience and an inevitability that nothing in human experience can match. The Great Attractor is not a mystery anymore, it is a place. But the scale of that place, the sheer size of the volume it influences, and the distance it reaches across, is something that demands to be reckoned with. It is not enough to know that it is there. You have to understand how far there is. And once you do, once the scale clicks into place, the next question becomes obvious. What is it made of? What kind of mass produces a pull that strong, that far-reaching, that persistent? The answer is not as simple as pointing to a cluster or a supercluster and saying, there it is, because most of the mass responsible for the Great Attractor is not visible. It is not stars or gas or galaxies. It is something else, something we have never directly observed, but know must be there, because nothing else explains the motion. That is where the story goes next. The maps told you where it was. The motion told you it was pulling. The scale told you how far that pull reached and how many galaxies were caught in it. But none of that tells you what it is. Not really. Not in the way you would like, where you could point to a picture and say, there, that object, that structure, that thing. The Great Attractor is not cooperating. Most of it is invisible. Not hidden behind dust this time, though that is still a problem. Invisible in a more fundamental sense. The mass responsible for the gravitational pull, the matter doing the actual pulling, does not emit light. It does not absorb light. It does not interact with light in any way we can detect. You cannot see it with a telescope, no matter what wavelength you observe in. You cannot photograph it. You cannot measure its temperature or its chemical composition or its distance using any of the standard tools of astronomy. The only reason we know it is there at all is because of what it does to the things around it. It pulls. And the strength of that pull tells us there is far more mass in the Great Attractor region than the visible galaxies and gas and stars can account for. Far more. The missing mass is not a rounding error, it is the majority. And that missing mass has a name: dark matter. Dark matter is not a new idea. Astronomers have been arguing about it since the 1930s, when a Swiss physicist named Fritz Zwicky studied the Coma cluster, a large collection of galaxies about 300 million light-years away. Zwicky measured the velocities of the galaxies in the cluster and did a straightforward calculation. If you know how fast the galaxies are moving, and you assume they are held together by gravity, you can estimate the total mass of the cluster. It is basic Newtonian mechanics. The faster the galaxies are moving, the more mass you need to keep them from flying apart. Zwicky's calculation gave him a number for the total mass, and when he compared that to the mass he could actually see in the form of stars and gas, the two did not match, not even close. The visible mass was only a small fraction of what the gravity required. There was mass missing, a lot of it. Zwicky called it dunkel materia, dark matter, and suggested that most of the cluster's mass was in some form that did not shine. Nobody believed him, not at first. Zwicky was a difficult personality, famously combative, and his result was so far outside the expectations of the time that most astronomers assumed he had made a mistake. Maybe his velocity measurements were wrong. Maybe the cluster was not in equilibrium. Maybe Newtonian gravity did not apply on those scales. The idea that the universe was filled with invisible matter that outweighed everything we could see was too strange to take seriously. It sounded like science fiction. So the results sat on the shelf for decades, cited occasionally, mostly ignored. Then in the 1970s, an astronomer named Vera Rubin started measuring the rotation curves of spiral galaxies. A rotation curve is a graph showing how fast stars and gas are moving at different distances from the center of a galaxy. If most of the mass in a galaxy is concentrated in the visible stars and bulge at the center, you would expect the rotation speed to drop off as you move farther out, the same way planets farther from the Sun orbit more slowly than planets closer in. That is what Newtonian gravity predicts. That is not what Rubin found. The galaxies she studied were rotating too fast. Stars and gas clouds at the outer edges of the galaxies were moving just as fast, sometimes faster, than material closer to the center. That should not happen unless there is more mass farther out. But there was no visible mass farther out. The stars thinned out. The gas thinned out. The light dropped off. And yet the rotation speeds stayed high, as if the galaxies were embedded in halos of invisible matter that extended far beyond the visible edges. Rubin measured galaxy after galaxy, and the pattern held. Every spiral galaxy she looked at had the same problem. The visible mass was not enough to explain the observed rotation. There was something else, something dark. By the 1980s, the evidence for dark matter had piled up to the point where ignoring it was no longer tenable. Observations of galaxy clusters, gravitational lensing, the large-scale structure of the universe, all of it pointed to the same conclusion. The matter we can see, the stars and gas and dust, makes up only about 15% of the total matter in the universe. The other 85% is dark. It does not emit light. It does not absorb light. It does not reflect light. It interacts with ordinary matter only through gravity. That is it. Gravity is the only handle we have. Everything we know about dark matter comes from watching how it pulls on the things we can see. The Great Attractor is almost certainly dominated by dark matter. The visible matter in the region, the galaxies in the Norma cluster, and the other clusters nearby, the hot gas glowing in X-rays between those galaxies, adds up to a lot of mass. Thousands of galaxies, each one containing billions of stars. Clouds of gas heated to tens of millions of degrees, glowing bright enough to be detected by X-ray telescopes halfway across the universe. That is not nothing. But it is not enough. Not by a factor of 5 or 10. The gravitational pull required to explain the motion of galaxies across Laniakea, the strength of the flow toward the Great Attractor, demands far more mass than the visible matter provides. The difference has to be dark matter. There is no other explanation that fits the data. We do not know what dark matter is. That might sound like a cop-out, a failure of science, but it is just honest. Dark matter is not made of atoms. We know that because atoms interact with light. You shine light on an atom, and the electrons in the atom absorb or scatter the photons. That interaction leaves fingerprints in the spectrum, absorption lines or emission lines that tell you what elements are present and how much of them there is. Dark matter does not do that. No fingerprints, no lines, no interaction. So it is not ordinary matter. It is not protons and neutrons and electrons arranged into the familiar structures of chemistry and biology. It is something else. Particle physicists have proposed dozens of candidates over the years: weakly interacting massive particles, axions, sterile neutrinos, primordial black holes. Each one has its advocates, its theoretical framework, its predictions. None of them has been detected. The experiments designed to find dark matter particles are among the most sensitive ever built. Detectors buried deep underground, shielded from cosmic rays, cooled to near absolute zero, waiting for a dark matter particle to collide with an atomic nucleus and produce a tiny flash of light or a microscopic vibration. The detectors have been running for years, decades in some cases. They have not found anything, not yet. The lack of detection does not mean dark matter is not real. It just means it is harder to catch than anyone expected, or the particles are lighter than predicted, or rarer, or interacting even more weakly than the models assumed. The absence of evidence is frustrating but not fatal. Dark matter is still the best explanation we have for the observations. The rotation curves, the cluster velocities, the gravitational lensing, the large-scale structure of the universe. All of it points to the same invisible mass, the same gravitational signature, the same dark scaffolding holding the visible universe together. In the context of the Great Attractor, dark matter is not an exotic add-on. It is the foundation. The clusters we can see, Norma and the others, are sitting inside much larger halos of dark matter. Those halos are what contain most of the mass. The galaxies are just tracers, bright markers showing where the dark matter has piled up. Think of it like this. If you could see dark matter, if it glowed or reflected light the way ordinary matter does, the Great Attractor region would look completely different. The galaxies would shrink into tiny bright dots, scattered across a vast, diffuse cloud of dark matter, extending hundreds of millions of light years in every direction. The cloud would be denser in some places, thinner in others, shaped by billions of years of gravitational collapse and the flow of matter along filaments in the cosmic web. The galaxies would be embedded in that cloud, like raisins in a pudding, concentrated in the densest regions where the dark matter has pulled ordinary matter together and triggered the formation of stars. The visible structures we see are side effects. The dark matter is the main event. This flips the usual way of thinking about the universe. We are used to assuming that the things we can see are the things that matter. The stars, the galaxies, the glowing nebulae, all of it seems so substantial, so real, that it is hard to accept that most of the universe is made of something we cannot detect. But the evidence is overwhelming. Dark matter is not a placeholder. It is not a fudge factor introduced to make the equations work. It is a physical substance, whatever that substance turns out to be, and it outweighs ordinary matter by a ratio of roughly 5:1. For every kilogram of stars and gas and dust, there are 5 kilograms of dark matter. That ratio holds everywhere we look. In galaxies, in clusters, in the cosmic web, in the Great Attractor. The visible universe is a minority. The dark universe is the majority. And understanding the Great Attractor means understanding how dark matter behaves on the largest scales, how it clumps and flows and pulls, how it shapes the gravitational landscape that drives the motion of everything we can see. The gravitational pull of the Great Attractor is not uniform. It is not a single point source like a star or a black hole. It is a distributed mass, spread across a region hundreds of millions of light years wide, clumped into clusters and filaments, separated by voids. The strength of the pull depends on where you are. Galaxies closer to the center feel a stronger tug. Galaxies farther out feel a weaker tug. Galaxies on the far side of Laniakea, near the boundary where the flow changes direction, are barely affected. The gravitational field is complex, shaped by the overlapping influences of multiple clusters, each one sitting in its own dark matter halo, each one contributing to the total pull. Mapping that field requires measuring the velocities of thousands of galaxies and using those velocities to reconstruct the underlying mass distribution. It is forensic work. You are inferring the presence of mass from its effect on motion, the same way you might infer the shape of a pond by watching ripples spread across the surface. That reconstruction is still incomplete. We have a rough picture. We know where the densest concentrations of mass are. We know where the filaments are. We know where the voids are. But the details are fuzzy because the data is noisy. Distance measurements have uncertainties. Velocity measurements have uncertainties. The galaxies themselves are not passive tracers. They have their own internal motions, their own interactions with neighbors, their own histories of mergers and collisions that add noise to the signal. Disentangling the large-scale flow from the local chaos is hard. It requires large samples, careful statistical analysis, and a willingness to accept that your map will always be an approximation. The Great Attractor is there, the pull is real, but the exact distribution of mass responsible for that pull is still being worked out. One of the complications is that the Great Attractor is not the only mass concentration affecting galaxy motions in this part of the universe. Beyond the Great Attractor, about 650 million light-years away, sits the Shapley Supercluster, one of the most massive concentrations of galaxies in the nearby universe. Shapley contains dozens of rich galaxy clusters spread across a region roughly 300 million light-years across. Its total mass is staggering, several times the mass of the Great Attractor region, and its gravity reaches far. Some studies suggest that the motion of the Milky Way and our local neighborhood is not just a simple fall toward the Great Attractor. It is a more complicated flow shaped by both the Great Attractor and Shapley, with Shapley pulling from beyond and the Great Attractor acting as an intermediate step. The flow is not toward a single point. It is toward a line, a gravitational axis stretching from here to Shapley, with the Great Attractor sitting somewhere in the middle. This complicates the story. The idea of a single dominant attractor pulling everything toward it is clean, simple, easy to picture. The reality is messier. The gravitational landscape is shaped by multiple structures, each one contributing to the total field, each one pulling on the galaxies around it. The Great Attractor is the most prominent feature in our immediate neighborhood, the structure closest to us that has a strong enough pull to dominate the local flow. But it is not isolated. It is part of a larger network, a chain of mass concentrations stretching across hundreds of millions of light-years. The motion of galaxies in Laniakea is the result of all those influences added together, weighted by distance and mass. Calling it the Great Attractor is shorthand, a label for the nearest, most obvious piece of a much larger puzzle. There is also the question of how much of the observed motion is actually caused by gravity and how much is left over from the initial conditions of the universe. When the Big Bang happened, matter was not distributed perfectly evenly. There were tiny fluctuations in density, regions that were slightly denser than average, and regions that were slightly less dense. Those fluctuations were the seeds of structure. Over billions of years, the denser regions grew denser, pulling in more matter, collapsing under their own gravity. The less dense regions grew less dense, emptied out as matter drained into the surrounding overdensities. That process shaped the cosmic web. But it did not erase the initial velocities. Galaxies today are moving partly because they are being pulled by gravity, and partly because they were already moving in a certain direction when they formed. Disentangling those two components is not straightforward. The motion we observe is a combination of gravitational infall and primordial momentum, and figuring out how much of each requires detailed modeling and comparison with simulations. Dark energy enters the picture here, though not in the way you might expect. Dark energy is not pulling, it is pushing, or more accurately, it is causing space itself to expand at an accelerating rate. Dark energy is the reason the universe is not just expanding, but expanding faster over time. Discovered in the late 1990s through observations of distant supernovae, dark energy makes up about 70% of the total energy content of the universe. It is everywhere, diffuse, uniform, and it acts like a kind of anti-gravity, a repulsive force that pushes space apart. On small scales, inside galaxies, or even inside galaxy clusters, dark energy is negligible. Gravity wins. Matter clumps together, forms structures, stays bound, but on the largest scales, across hundreds of millions or billions of light-years, dark energy dominates. It drives the expansion. It pulls the cosmic web apart, slowly but inexorably, stretching the filaments, enlarging the voids, carrying distant galaxy clusters away from each other faster and faster as time goes on. The Great Attractor is fighting against that expansion. Right now, gravity is winning. The galaxies in Laniakea are flowing toward the Great Attractor, pulled by the combined mass of the region, moving against the expansion of space. But that will not last forever. Eventually, the expansion will overcome the gravitational pull. The outer edges of Laniakea will drift away, carried off by the accelerating expansion, and the flow will reverse. The timescale for that reversal is tens of billions of years, far longer than the current age of the universe. For now, the Great Attractor is still a gravitational anchor, still pulling, still shaping the motion of galaxies across hundreds of millions of light-years. But dark energy is patient. On cosmic timescales, it will win. The structures we see today, the clusters and superclusters and filaments, are temporary. They are snapshots of a process that is still unfolding, a tug-of-war between gravity pulling matter together and dark energy pulling space apart. The outcome of that war is not in doubt. Expansion wins, but the contest takes billions of years, and we are watching it unfold in the middle. Dark matter and dark energy are not the same thing. That confusion comes up often enough that it is worth addressing head-on. The names are similar, and both are invisible, but they are completely different phenomena. Dark matter is matter. It has mass. It pulls. It clumps into structures, forms halos around galaxies, shapes the cosmic web. It behaves like ordinary matter in the sense that it responds to gravity and exerts gravity. It just does not interact with light. Dark energy is not matter. It is energy, a property of space itself, uniform and diffuse, and it pushes. It does not clump. It does not form structures. It is the same everywhere, a constant background pressure driving the expansion of the universe. The two are related only in the sense that they both involve things we cannot see and do not fully understand, but their effects are opposite. Dark matter pulls, dark energy pushes, and the balance between them determines the fate of the universe. In the context of the Great Attractor, dark energy is the reason the structure will not last forever. The gravitational pull is strong, but it is not strong enough to hold the entire supercluster together indefinitely. Only the densest regions, the massive clusters like Norma, will remain bound. The rest will disperse, carried off by the expansion. Dark matter is the reason the gravitational pull exists in the first place. Without dark matter, the visible mass in the region would not be enough to produce the observed flow. The galaxies would be drifting more slowly, the pull would be weaker, and the structure would be less prominent. Dark matter is the hidden scaffolding. Dark energy is the force tearing the scaffolding apart. Both are critical to understanding the Great Attractor, but their roles are different. The search for dark matter continues. Particle physicists are still building detectors, still running experiments, still hoping for a direct detection. Astronomers are still mapping the distribution of dark matter in galaxies and clusters, using gravitational lensing to see where the mass is concentrated, using galaxy velocities to trace the flow. Each new observation adds a piece to the puzzle. Each new simulation refines the models. The picture that is emerging is one of a universe dominated by invisible components, where the matter we can see is just the tip of the iceberg, and the forces shaping the cosmos operate on scales far larger than anything we experience in daily life. The Great Attractor is part of that picture. It is a node in the cosmic web where dark matter has piled up, where gravity has taken hold, where the flow of galaxies converges. It is not unique. The universe is full of such nodes, but it is ours. It is the one close enough to affect us, close enough to measure, close enough to study in detail. And studying it means studying dark matter, means grappling with the fact that most of the universe is invisible, means accepting that the tools we have, The telescopes and detectors and equations are only good enough to see the effects, not the cause. We see the pull, we see the motion, we see the galaxies falling, but the thing doing the pulling, the dark matter itself, remains hidden. Not because it is far away, not because it is obscured by dust or blocked by the Milky Way. Hidden because it does not interact with light. Because it is fundamentally, irreducibly dark. That invisibility is frustrating. It is also humbling. We have built a model of the universe that works. It explains the observations. It predicts new phenomena that are later confirmed. It fits the data. But the model is built on components we cannot see and do not fully understand. Dark matter, dark energy. Together they make up 95% of the universe. Ordinary matter, the stuff we are made of, the stuff stars are made of, the stuff we can actually detect and measure and touch, is 5%. We are the minority, we are the exception. And the structures we live in, the galaxies and clusters and superclusters, are shaped primarily by the invisible 95%. The Great Attractor is proof of that. Its pull is too strong, its influence too widespread to be explained by visible matter alone. The dark matter is there, has to be there, piled up in halos around the clusters, filling the filaments, shaping the flow. We cannot see it. We can only measure its effects, and those effects are enormous. The ongoing search for dark matter is not just about solving a physics problem. It is about understanding the universe we live in, about figuring out what most of the cosmos is made of, about closing the gap between the 5% we can see and the 95% we cannot. Every galaxy survey, every velocity measurement, every lensing observation adds to that effort. The Great Attractor is one of the best laboratories we have for studying dark matter on large scales. It is close enough to map in detail. It is massive enough that the effects are strong and clear. It is part of our local neighborhood, part of the structure we are embedded in. Studying it means studying ourselves, figuring out where we are, what we are moving toward, what forces are shaping our motion through space, and all of that traces back to dark matter, to the invisible mass holding the cosmic web together, to the pull we can measure but cannot see. The identity of the Great Attractor, then, is not a simple answer. It is not a single object you can point to and catalogue. It is a region, a gravitational basin carved out by the combined influence of multiple clusters and their dark matter halos. The most prominent visible component is the Norma cluster, sitting near the calculated center of the pull. But Norma is just the brightest piece. The dark matter extends far beyond it, diffuse and invisible, shaping the gravitational field across hundreds of millions of light-years. The shapely supercluster pulls from beyond, adding its own influence, complicating the flow. And dark energy, the background pressure driving cosmic expansion, is slowly working to tear the whole structure apart. The Great Attractor is all of that. A node in the cosmic web, a concentration of dark matter, a convergence point for galaxy flows, a temporary feature in a universe that is still expanding, still evolving, still playing out the consequences of the Big Bang. It is not a thing, it is a place. And the thing pulling us toward that place is mostly invisible, detectable only through the motion it causes, the flow it drives, the tug we can measure but cannot see. That tug is real, the pull is happening right now. And at 600 kilometers per second, we are falling toward it, whether we understand it or not. That motion, that inevitable drift, is where the story goes next. 600 kilometers per second. That is how fast the Milky Way is falling toward the Great Attractor. Not drifting, not coasting, falling, pulled by gravity across a distance so vast that the human brain has no framework to process it. 600 kilometers every second. While you read that sentence, you traveled several thousand kilometers through space. While you took your last breath, you moved hundreds of kilometers closer to a gravitational center you will never see, located in a direction you cannot point to, sitting behind a wall of dust and stars that has been blocking our view since before humans existed. And this has been happening your entire life. It was happening before you were born. It will keep happening long after you are gone. The Milky Way has been falling toward the Great Attractor for billions of years, and it will keep falling for billions more. And here is the strangest part. We will never get there. 600 kilometers per second is not a speed that means anything to human intuition. You can say the number, you can write it down, you can do the math, but your brain does not have a reference point for motion at that scale. So let us build one. Start small. A car on a highway travels at about 100 kilometers per hour. That is fast enough that you feel the acceleration when you press the gas pedal. Fast enough that a crash will kill you. Fast enough that covering a few hundred kilometers in an afternoon feels like an accomplishment. The Milky Way is moving at 600 kilometers per second, not per hour, per second. That is 16 million kilometers per hour. Or if you prefer, about 3 million miles per hour. Take the fastest car you have ever been in and multiply its speed by 20,000. That is how fast you are moving right now, sitting still, reading this, thinking you are stationary. You are not stationary. You are falling through space faster than anything you have ever experienced, and you cannot feel it. The Earth orbits the Sun at about 30 kilometers per second. That is already fast. Fast enough that if you could somehow stop the Earth in its orbit, it would fall straight into the Sun in a matter of months. Fast enough that covering the 150 million kilometers between the Earth and the Sun takes a full year. The Milky Way is moving 20 times faster than that. 20 times the speed at which the Earth circles the Sun, and it is carrying the Sun, the Earth, and everything else in the galaxy along with it. You are not just orbiting the Sun, you are falling toward the Great Attractor. Both motions are happening simultaneously, layered on top of each other like currents in an ocean. The Earth circles the Sun circles the center of the Milky Way, and the Milky Way falls toward a point in space 250 million light-years away, pulled by the gravity of tens of thousands of galaxies piled into one region. At 600 kilometers per second, you could travel from the Earth to the Moon in a little over a minute. The Moon sits about 384,000 kilometers away. Divide that by 600 and you get 640 seconds, 10.5 minutes. A beam of light makes the trip in about 3 seconds. You, riding along with the Milky Way's motion toward the Great Attractor, would get there in 10 minutes. You could cover the distance between the Earth and the Sun, 150 million kilometers, in less than 3 days. The Voyager 1 spacecraft, the fastest human-made object to leave the solar system, took more than 35 years to reach the edge of the Sun's influence. At 600 kilometers per second, you would pass Voyager's current position in about a week. That is the scale of the motion. That is how fast we are falling. And yet, you feel nothing. There is no wind in your face, no acceleration pressing you back into your seat, no sense of motion at all. That is because everything around you is moving at the same speed. The ground beneath your feet, the air you breathe, the moon in the sky, the sun overhead, all of it is falling together, carried along by the motion of the galaxy as a whole. Motion is relative. You only feel acceleration when something pushes or pulls on you relative to your surroundings. If everything is accelerating together, there is no relative motion to detect. You are in free fall, the same way an astronaut on the International Space Station is in free fall, constantly falling toward the Earth, but moving sideways fast enough that they keep missing it. The Milky Way is in free fall toward the Great Attractor, and because everything in the galaxy is falling together, there is no way to feel it. The only reason we know it is happening at all is because we can measure the motion of other galaxies and compare them to ours. We can see that we are moving relative to the cosmic microwave background, the faint afterglow of the Big Bang that fills the entire universe. That background is as close to a universal reference frame as we have, and relative to that frame, we are moving at 600 kilometers per second toward the Great Attractor. This is not a new discovery. Astronomers have known about the motion since the 1970s, when they first started measuring the peculiar velocities of galaxies in the local universe, and noticed that everything in a huge region of space was drifting in the same direction. The velocity itself was pinned down more precisely in the 1980s, and the direction was identified as pointing toward a region of the sky in the southern hemisphere, hidden behind the plane of the Milky Way. The number, 600 kilometers per second, has been refined over the decades as measurements improved, but it has not changed dramatically. We are moving at roughly that speed. We have been moving at roughly that speed for billions of years, and barring some catastrophic event that disrupts the structure of the galaxy, we will keep moving at roughly that speed for billions of years to come. The journey is silent. There is no engine, no fuel, no thrust. Just gravity, patient and inexorable, pulling the galaxy along a path carved out by the distribution of mass across hundreds of millions of light years. The Great Attractor does not reach out and grab us. It does not send tendrils of force across space to haul us in. It just sits there, massive and dense, warping the fabric of space around it, and we slide down the slope it creates. Think of it like a marble rolling toward the bottom of a bowl. The bowl is not pulling the marble. The shape of the bowl, the curvature of its surface, is what guides the motion. The marble rolls because that is the path of least resistance. The Milky Way is the marble. The Great Attractor is the bottom of the bowl, and the slope we are rolling down stretches across 250 million light-years of space. At 600 kilometers per second, how long would it take to reach the Great Attractor? The math is simple. Distance divided by speed. 250 million light-years is about 4 times 10 to the 21st kilometers. Divide that by 600 kilometers per second, and you get roughly 4 times 10 to the 18th seconds. Convert that to years, and you get about 127 billion years. The universe is currently 8 billion years old. We have been falling toward the Great Attractor for a significant chunk of that time, probably several billion years at least. And if the motion continued unchanged, we would keep falling for another 127 billion years before we arrived. That is nearly 10 times the current age of the universe. The sun will have died. The Earth will have been consumed or flung out of the solar system. The stars in the Milky Way will have burned through their fuel and faded into cold remnants, and we will still be falling, except we will not be, because the universe is not static. It is expanding, and that expansion is accelerating. On scales larger than a few hundred million light-years, the expansion of space itself overwhelms the gravitational pull of local structures. Galaxies that are far enough apart are being carried away from each other by the stretching of space, and the rate at which they are separating is increasing over time. This is the effect of dark energy, the mysterious force that makes up about 70% of the universe and drives the accelerating expansion. Dark energy is weak. On the scale of a galaxy or even a galaxy cluster, it is negligible. Gravity wins. Matter clumps together, structures form, things stay bound. But on the scale of superclusters, across hundreds of millions or billions of light years, dark energy dominates. It pulls space apart faster than gravity can pull matter together. And that means the Great Attractor, despite its enormous mass and the strength of its gravitational pull, is not strong enough to hold the entire structure together indefinitely. The flow we are part of, the motion of 100,000 galaxies across Laniakea toward the Great Attractor, is a temporary phenomenon. It is real, it is happening right now, but it is not permanent. Over the next few tens of billions of years, the expansion of the universe will stretch the distances between galaxies in Laniakea faster than they are falling toward the center. The outer edges of the supercluster will drift away first, carried off by the expansion, their motion reversing as dark energy overcomes the gravitational pull. The flow will weaken, the basin of attraction will shrink. Eventually, only the densest regions, the massive clusters like Norma and the structures immediately surrounding them, will remain bound. The rest will disperse, scattered across an expanding universe, their connections to the Great Attractor severed. The journey we are on, the 600 km/s drift toward a gravitational center 250 million light-years away, will not end in arrival. It will end in dissolution. The destination will recede faster than we can approach it. The expansion will win. This is not speculation. It is prediction based on observations of how the universe is behaving right now. The expansion of the universe was discovered in the 1920s by Edwin Hubble, who found that distant galaxies were moving away from us, and that the farther away they were, the faster they were receding. That relationship, velocity proportional to distance, is the signature of an expanding universe. For most of the 20th century, astronomers assumed the expansion was slowing down, gradually decelerated by the gravitational pull of all the matter in the universe. Then in 1998, two independent teams measuring the distances and redshifts of distant supernovae found something unexpected. The expansion was not slowing down, it was speeding up. Distant galaxies were receding faster than the models predicted. Something was pushing space apart, and that something was uniform, diffuse, and pervasive. They called it dark energy. The discovery won a Nobel Prize. It also upended the assumptions about the universe's future. Before dark energy, the question was whether the universe would expand forever or eventually collapse back on itself. Would gravity win, pulling everything back together into a big crunch? Or would the expansion continue indefinitely, carrying galaxies farther and farther apart until the universe grew cold and dark and empty? The discovery of dark energy answered that question. The expansion will continue. It will accelerate. Galaxies that are not gravitationally bound to each other will drift apart faster and faster until they are separated by distances so vast that light from one will never reach the other. The observable universe will shrink. The cosmic web will dissolve. The clusters that remain bound will become isolated islands in an ever-expanding sea of space, and eventually even those clusters will fade. Stars will burn out. Black holes will evaporate. The universe will approach a state of maximum entropy, a cold, dark, featureless expanse where nothing happens and nothing ever will. That fate is trillions of years away. For now, the universe is still young, still dynamic, still full of structure and motion and activity. The Great Attractor is still pulling. The galaxies in Laniakea are still falling. The motion we are part of is real, measurable, and ongoing, but it is temporary. We are watching a process that will eventually reverse, a flow that will eventually stop, a structure that will eventually dissolve. The inevitability is not arrival, it is dispersal. We are falling toward a place we will never reach, There is something profoundly unsettling about that realization. Humans are used to journeys that have destinations. You get in a car, you drive, you arrive, you board a plane, you fly, you land. Even the longest journeys, the ones that take months or years, have endpoints. But the motion of the Milky Way toward the Great Attractor is a journey without an endpoint. It is motion for its own sake, driven by forces that operate on timescales so long that the concept of arrival becomes meaningless. We are falling, and we will keep falling, but the place we are falling toward will recede into the distance faster than we can approach it. The journey is the only thing that matters. The destination is irrelevant. This is not unique to the Great Attractor. It is a feature of the universe we live in. On the largest scales, cosmic expansion dominates. Structures that are not gravitationally bound will drift apart. Galaxies that are far enough away will recede faster than the speed of light, not because they are moving through space that fast, but because the space between us and them is expanding. The light they emit will never reach us. They will disappear from view, not because they stopped existing, but because the universe stretched the distance between us beyond the point where light can ever close the gap. The observable universe is shrinking, not because the universe itself is getting smaller, but because the expansion is carrying distant objects over a horizon we can never cross. And the motion we are part of, the drift toward the Great Attractor, is just one small current in a much larger flow. A flow that is being slowly, inexorably torn apart by the expansion of space itself. The timescale matters. 127 billion years to cover the distance to the Great Attractor at our current speed. That number is so large, it might as well be infinite. The Sun has existed for about 4-6 billion years. It will continue burning for another 5 billion years or so before it exhausts its fuel and expands into a red giant, swallowing the inner planets and ending any possibility of life on Earth. The Milky Way and Andromeda are on a collision course, moving toward each other at about 110 kilometers per second. They will merge in about 4 to 5 billion years, creating a new, larger galaxy that astronomers have playfully dubbed Milky Way. That merger will reshape the structure of both galaxies, flinging stars into new orbits, triggering bursts of star formation, and fundamentally altering the gravitational environment of everything within them. And even after that merger, even after the Milky Way and Andromeda have combined into a single structure, the resulting galaxy will still be falling toward the Great Attractor. The motion will not stop. It will just continue under a different name, with a different set of stars, in a universe that has continued to age and expand. But 127 billion years is far beyond that. It is far beyond the timescale on which stars burn. It is far beyond the timescale on which galaxies evolve. It is deep into the era when the universe will be dominated by dark energy, when the expansion has stretched distances so far that most galaxies will have disappeared over the cosmic horizon, when the clusters that remain bound will be isolated oases in a vast, empty expanse. By the time 127 billion years have passed, the Great Attractor will no longer exist as a coherent structure. The clusters that make it up will have dispersed, the dark matter halos will have thinned out. The gravitational pull will have weakened to the point where it is irrelevant. The destination we are falling toward will have dissolved into the expanding void. And yet, the motion is real. Right now, this moment, the Milky Way is moving at 600 kilometers per second. The pull is active. The fall is ongoing. The fact that the journey will never be completed does not make the motion any less real. It just makes it futile in a way that human minds struggle to process. We are used to thinking of motion as purposeful, as directed toward a goal. A car drives to a destination, a plane flies to a city, a ship sails to a port. But the motion of galaxies is not purposeful. It is not directed by intention or design. It is the result of gravity acting on mass distributed unevenly across space, playing out over billions of years, indifferent to whether anything ever arrives anywhere. The universe does not care about destinations. It cares about forces and masses and the geometry of space. And those forces and masses and geometries have set the Milky Way on a path that will continue for longer than most structures in the universe will last. There is a certain beauty in that futility. The motion is not wasted, it is not meaningless. It is part of the process, part of the unfolding of the universe from its initial conditions through the present and into the distant future. The fact that the journey has no endpoint does not diminish the fact that it is happening. The Milky Way is falling. The galaxies in Laniakea are falling. The Great Attractor is pulling. And that pull, that motion, that silent drift through space at 600 kilometers per second is shaping the structure of the universe on the largest scales. It is carving out the flow patterns that define superclusters. It is organizing the cosmic web. It is connecting us to structures hundreds of millions of light years away, binding us into a network of matter and gravity that stretches across distances no human will ever traverse. The motion is the point. The journey is the thing that matters. The destination was always a mirage, 600 kilometers per second, faster than anything you have ever experienced. Faster than any vehicle humans have ever built, faster than the Earth orbits the Sun, fast enough to cross the distance to the Moon in 10 minutes, fast enough to reach the edge of the solar system in days, and yet slow enough that covering the distance to the Great Attractor would take longer than the universe has existed. That is the paradox. That is the tension. Motion that is both staggering and insignificant, both overwhelming and futile, both real and ultimately irrelevant. We are falling, and we will keep falling, and we will never arrive. The Great Attractor will recede, the expansion will win, the structure will dissolve. And billions of years from now, long after the sun has died and the stars have faded and the galaxies have scattered, the motion we are part of today will be a footnote, a faint echo of a process that ran its course and ended in dispersal. But that is billions of years from now. For now, the motion is real, the pull is active, the journey is ongoing. And every second of every day, the Milky Way moves another 600 kilometers closer to a destination it will never reach. That motion connects us to the largest structures in the universe. It reminds us that we are not isolated, not adrift in a featureless void, but part of a web, a network, a flow that has been running for billions of years and will continue for billions more. The Great Attractor is pulling. We are falling. And the fact that we will never get there does not change the fact that we are on the way. The journey is silent, unyielding, and inevitable. And it is carrying us, along with 100,000 other galaxies, toward a place that exists only as a gravitational shadow, a concentration of dark matter hidden behind dust and stars, invisible but undeniable. The motion is the story, the speed is the evidence, and the futility, the knowledge that the destination will dissolve before we arrive, is the final twist. We are falling towards something that will not be there when we reach it, but we are falling nonetheless, 600 kilometers per second, every second, forever, until the expansion tears it all apart. And yet, even as this futile drift continues, even as we slide down the gravitational slope toward a center that will eventually vanish, the universe is not done surprising us. Because beyond the Great Attractor, beyond the clusters and superclusters and the flows we have mapped, there are larger structures still. voids so vast they dwarf everything we have talked about so far. Regions of space where almost nothing exists, separated by walls of galaxies stacked in sheets and filaments. The cosmic web extends far beyond Laniakea, far beyond the Great Attractor, into a landscape so large and so strange that it forces us to reconsider what we mean when we talk about the universe itself. The motion we are part of is just one current in a much larger ocean. And that ocean, it turns out, has depths we are only beginning to explore. The Great Attractor is not the end of the story. It is not even close. It is a node, one intersection in a network that stretches across billions of light years in every direction. The cosmic web, that three-dimensional lattice of filaments and clusters and voids, does not stop at the boundaries of Laniakea. It continues. Other superclusters, other flows, other gravitational basins, all interconnected, all part of the same vast structure. And the thing about a web is that it is defined as much by what is missing as by what is there. The strands matter, but so do the gaps between them, the voids. Cosmic voids are not empty in the absolute sense. There is always something. A few stray galaxies, wisps of gas. Dark matter, probably, though mapping it in voids is difficult because there is so little ordinary matter to trace. But voids are empty enough that calling them empty is not misleading. They are regions of space, sometimes hundreds of millions of light years across, where the density of matter is far below the cosmic average. If the average density of the universe is 1, a void might be 0.1 or 0.01, underdense by a factor of 10 or 100, not because matter was destroyed or removed, but because it drained out. Gravity pulled it away toward the filaments and clusters surrounding the void, leaving behind a hollow. The voids are not small. The Buta's void, one of the first large voids discovered, spans roughly 330 million light-years. It was identified in 1981 by astronomers conducting a survey of galaxy redshifts. They were expecting to find galaxies distributed more or less evenly across the volume they were mapping. Instead, they found a region where galaxies were almost completely absent. A hole in the distribution so large it took years for the community to accept that it was real. Since then, dozens of other voids have been mapped. The local void, sitting just outside the local group, about 150 million light-years across. The Sculptor void, the Eridanus supervoid. Some are larger than the Buta's void, some are smaller, but all of them are enormous, and all of them are part of the same pattern. The cosmic web is a network of dense filaments surrounding vast empty regions. The filaments are where the galaxies are, the voids are where they are not. The existence of voids changes how we think about the Great Attractor. It is not just a pile of mass sitting in space, pulling on everything around it. It is a node in a network, surrounded by filaments that feed matter into it from the surrounding regions, and those regions include voids. The voids are not passive, they are part of the structure. Matter does not just fall toward overdense regions, it also drains away from underdense regions. The voids push, in a sense. Not with an active force, not with some kind of anti-gravity, but by being empty, by having less mass than their surroundings, they create a pressure gradient. Galaxies on the edge of a void are pulled more strongly toward the denser filaments and clusters than they are pulled back toward the void. The result is a net motion away from the void toward the walls. The void acts like a repeller. That term, repeller, has gained traction in recent years as astronomers have worked to map not just where galaxies are, but how they are moving. The flow of galaxies across the cosmic web is driven by both attractors and repellers. Attractors pull, repellers push. Or more accurately, attractors pull more strongly and repellers pull less strongly. And the difference in gravitational potential creates currents that drive galaxies from underdense regions toward overdense ones. The Great Attractor is an attractor, but it is surrounded by repellers, voids, and underdense regions that contribute to the flow by pushing galaxies away from themselves and toward the denser structures nearby. The most prominent repeller in our local neighborhood is called the dipole repeller. It was identified in 2017 by a team led by Yehuda Hoffman at the Hebrew University of Jerusalem. The dipole repeller is not a void in the traditional sense. It is a low-density region sitting roughly opposite the direction of our motion toward the Great Attractor. The idea is that our motion, the 600 kilometers per second drift of the Milky Way through space, is not just caused by the pull of the Great Attractor and the Shapley Supercluster ahead of us. It is also caused by the push of the dipole repeller behind us. We are being pulled forward and pushed from behind simultaneously. The name dipole comes from the fact that the motion has two poles, two centers of influence acting in opposite directions. One pulls, one pushes, and together they drive the flow. This is not a new idea in principle. Astronomers have understood for decades that the motion of galaxies is shaped by the full gravitational field, not just by individual attractors. But mapping that field, identifying specific repellers, and understanding their contributions is harder than mapping attractors because repellers are defined by the absence of mass rather than its presence. You have to survey large volumes of space, measure the positions and velocities of thousands of galaxies, and reconstruct the density field to see where the underdense regions are and how they are affecting the flow. The dipole repeller was the first such structure to be named and studied in detail, but it is not the only one. The cosmic web is full of voids, and every void is a repeller in the sense that its low density creates a gradient that pushes nearby galaxies away. The balance between attractors and repellers is what shapes the web. Galaxies flow from voids into filaments, from filaments into clusters, from clusters into superclusters. The flow is not random. It is organized, driven by the distribution of mass and the geometry of space. The Great Attractor sits at a convergence point, a place where multiple filaments meet and the flow from several directions comes together. But it is not the only such point. The Shapley Supercluster, sitting about 650 million light-years away, is another convergence point. Larger, more massive, pulling on galaxies across an even wider region, and beyond Shapley there are other structures, other superclusters, other nodes in the web. The pattern repeats over and over across the entire observable universe. This raises a question that has been lurking in the background for the entire discussion. Is there something even larger? Some structure beyond superclusters, some organization of matter on scales so vast that we have not yet been able to map it? The short answer is maybe. The longer answer is complicated. There are hints, suggestions, anomalies in the data that could point to structures larger than superclusters. But the evidence is not conclusive, and the theoretical framework for understanding such structures is still being worked out. One of the challenges is that the larger the structure, the harder it is to see. Mapping the cosmic web requires measuring the positions and velocities of galaxies across huge volumes of space. The farther away a galaxy is, the harder it is to measure its distance accurately, and the noisier the data becomes. Superclusters like Laniakea and Shapley are at the edge of what we can map with current techniques. Structures larger than that would require surveys that cover even larger volumes with even more galaxies, and the uncertainties would be even larger. It is not impossible, it is just difficult. And the data we have so far does not give a clear answer. there are some intriguing hints. The Hercules Corona Borealis Great Wall, identified in 2013, is a structure that spans roughly 10 billion light-years, making it one of the largest known structures in the universe. It is not a wall in the literal sense. It is a concentration of galaxy clusters and superclusters that appear to be aligned along a filament or sheet stretching across a huge fraction of the observable universe. If the structure is real, and that is still debated, it would be larger than anything the standard model of cosmology predicts should exist. Structures that large should not have had time to form in the age of the universe. The fact that they might exist anyway is a problem. It suggests either that the observations are being misinterpreted or that something about the standard model needs to be revised. Another hint comes from studies of the cosmic microwave background, the faint afterglow of the Big Bang. The temperature of that radiation is almost perfectly uniform across the sky, but there are tiny fluctuations, differences of a few parts in 100,000, that reflect the density variations in the early universe. Those fluctuations are the seeds of structure. The regions that were slightly denser became the clusters and superclusters we see today. The cosmic microwave background maps those seeds in exquisite detail, and for the most part, the patterns match what the standard model predicts. But there are anomalies. A large cold spot in the southern hemisphere that is colder and larger than expected. Alignments in the fluctuations that seem to point in preferred directions, even though the universe should be statistically isotropic, the same in all directions. Some of these anomalies could be explained by voids or superclusters along the line of sight, structures that affect the temperature of the radiation as it passes through them. Others are harder to explain. The possibility that the universe contains structures larger than superclusters, or that the distribution of matter is less random and more organized on the largest scales than the models predict, is unsettling. It does not necessarily mean the models are wrong. It could mean we are still in the process of mapping the universe, still filling in the details, and the full picture has not come into focus yet. Or it could mean there is something missing from the standard model, some process or component that we have not accounted for. Either way, the question is open. And the Great Attractor, as prominent as it is in our local neighborhood, is just one small piece of a much larger puzzle. Then there is the multiverse. The idea that our universe, the entire observable cosmos, stretching 93 billion light-years from edge to edge, might be just one bubble in a much larger space. One region where the laws of physics and the constants of nature happen to have the values they do, surrounded by other regions where they are different. The multiverse is not a single theory. It is a family of ideas, some of them motivated by cosmology, some by quantum mechanics, some by string theory. The details vary, but the basic concept is that what we call the universe might not be everything. There might be other universes, other regions of space and time, separated from ours by barriers we cannot cross and distances we cannot measure. The multiverse is speculative. It has to be. By definition, if other universes exist and we cannot observe them, we cannot test the hypothesis directly. That makes it uncomfortable for a lot of physicists who prefer theories that make predictions you can verify. But the multiverse is not pulled out of thin air. It emerges naturally from several different lines of theoretical work. Inflation, the theory that the universe underwent a rapid expansion in the first fraction of a second after the Big Bang, predicts that different regions of space could inflate at different rates and end up as separate, disconnected universes. String theory, which attempts to unify gravity with the other forces of nature, predicts a vast landscape of possible vacuum states, each one corresponding to a different set of physical laws. Quantum mechanics, in some interpretations, suggests that every time a quantum event occurs, the universe splits into multiple branches, each one representing a different outcome. None of this has been proven. None of it may ever be provable, at least not in the way we usually think about proof in science. But the multiverse is taken seriously by a significant number of physicists because it solves certain problems and because it emerges from theories that have been successful in other contexts. And if the multiverse is real, it changes the way we think about the universe we live in. The Great Attractor, Laniakea, the cosmic web, all of it would be local structure, patterns that arose in this particular bubble of space because of the specific initial conditions and physical laws that apply here. In another bubble, another universe, the structure might look completely different, or there might be no structure at all, or the laws of physics might be so different that galaxies and stars and planets never form. The connection between the multiverse and the Great Attractor is not direct. The multiverse does not explain the Great Attractor. It does not tell us why there is a concentration of mass sitting 250 million light-years away, pulling on everything in Laniakea. What it does is provide context. It reminds us that the universe we observe, as vast and complex as it is, might be just one small region of a much larger reality. And the structures we see, the attractors and repellers and filaments and voids, are shaped by processes that may be playing out on scales far beyond what we can observe. The Great Attractor is local, the cosmic web is local, the observable universe is local. Local in the sense that it is just the part we can see, the part where light has had time to reach us since the Big Bang. Beyond that, beyond the cosmic horizon, there is more space, more galaxies, more structure. And if the multiverse is real, there is not just more, there is different. Other regions with other laws, other constants, other outcomes. This is where the story expands beyond the bounds of anything we can measure. The Great Attractor is real. We can map it, measure its effects, study the flow of galaxies toward it. The cosmic web is real. We can see its structure, trace its filaments, identify its voids. But the larger questions, the ones about what lies beyond the web, and whether there are other universes, and how our observable cosmos fits into a potentially infinite reality, are questions that science is only beginning to grapple with. And they may not have answers, at least not answers we can verify. That does not make them unimportant, it makes them profound. It makes them the kind of questions that push the boundaries of what we can know and force us to confront the limits of observation, the constraints of our position, the finitude of our perspective. Humanity has always been bad at accepting limits. We build telescopes to see farther. We launch spacecraft to reach beyond our planet. We construct mathematical models to describe things we cannot touch or visit or directly observe. The Great Attractor is a perfect example. A structure so far away that its light takes longer to reach us than complex life has existed on Earth, hidden behind a wall of dust and stars, invisible to optical telescopes, detectable only through the motion it causes in galaxies hundreds of millions of light-years away. And yet, we found it, we mapped it, we figured out what it is and how it fits into the larger structure of the universe. That is not a small achievement. It is a testament to persistence, to ingenuity, to the willingness to follow the data wherever it leads, even when the destination is strange and uncomfortable and far beyond the scale of anything human experience can grasp. The Great Attractor is not unique. The universe is full of such structures, nodes in the web, convergence points where matter has piled up and gravity has taken hold. What makes the Great Attractor special is that it is ours. It is close enough to affect us, close enough to measure, close enough to study. It is the gravitational anchor of our cosmic neighborhood, the center of the flow we are part of, the place we are falling toward, even though we will never arrive. And understanding it, mapping it, figuring out how it fits into the cosmic web has taught us more about the universe than almost any other single structure. It has shown us that the cosmos is not smooth or uniform or simple. It is structured, organized, shaped by gravity and dark matter and the expansion of space into a pattern that repeats across billions of light years. It has shown us that we are not isolated, not adrift in a featureless void, but part of a network, a flow, a web that connects us to structures far beyond anything we can see. And it has shown us something else. Something harder to articulate, but impossible to ignore once you sit with it long enough. The universe does not care about us. It does not care about our questions, or our models, or our desire to understand. It does what it does, following the laws of physics, playing out the consequences of the initial conditions set in motion at the Big Bang, indifferent to whether anyone is watching. The Great Attractor is pulling. The galaxies are falling. The voids are pushing. The web is evolving. And all of it is happening on scales so vast and over time scales so long that human civilization, human history, the entire span of time that humans have existed, is less than a blink. We are watching a process that has been running for billions of years and will continue for billions more. We are observers, witnesses, temporary participants in a cosmic ballet that does not need us and will not miss us when we are gone. That realization could be crushing. It could make everything we do feel small and pointless and irrelevant. Or it could be liberating. Because if the universe does not care, if our existence is not central to anything happening on the largest scales, then we are free to care on our own terms, free to find meaning in the search, in the questions, in the effort to understand even when understanding is difficult and incomplete. The Great Attractor does not exist to teach us anything. It is not a lesson or a message or a sign. It is just there, a concentration of mass shaped by gravity, pulling on galaxies because that is what gravity does. But we can learn from it anyway. We can study it, map it, figure out how it fits into the larger structure of the cosmos. And in doing that, we can learn something about ourselves, about what it means to be a species capable of asking questions that span hundreds of millions of light years, capable of detecting motion we cannot feel and mapping structures we cannot see, capable of sitting on a small planet orbiting an ordinary star in an unremarkable galaxy and figuring out that we are falling toward a place we will never reach. The cosmic web stretches beyond the Great Attractor, beyond Laniakea, beyond anything we have talked about in this story. It extends across the entire observable universe, connecting galaxies and clusters and superclusters into a single interconnected network. And beyond the observable universe, beyond the cosmic horizon, where light has not yet had time to reach us, the web continues. More galaxies, more clusters, more filaments and voids, all part of the same pattern, all shaped by the same forces, all participating in the same slow, patient evolution from the nearly uniform distribution of matter in the early universe to the richly structured cosmos we see today. The Great Attractor is one small node in that network. Laniakea is one small supercluster. The observable universe is one small bubble. And if the multiverse is real, even the entire universe is just one small region of a reality so vast and so varied that the words we use to describe it, words like large and infinite and incomprehensible, lose their meaning. We will never map the entire web. We will never see beyond the cosmic horizon. We will never visit another universe if other universes exist, but we can keep looking, we can keep measuring. We can keep asking questions and following the data and building models and testing predictions. We can keep pushing the boundaries of what we know, one observation at a time, one galaxy at a time, one structure at a time. The Great Attractor is part of that effort. It is a milestone, a landmark, a piece of the puzzle that fell into place after decades of work. And there are more pieces waiting to be found. More anomalies in the data. More structures hiding in the zone of avoidance or sitting just beyond the range of current surveys. More questions about how the web formed and how it will evolve and what it tells us about the universe as a whole. The universe is not done surprising us. It never will be, because no matter how much we learn, no matter how far we look, there is always more. More distance, more time, more structure, more complexity. The Great Attractor taught us that. It was hiding in plain sight for decades, obscured by dust, overlooked because it was hard to see, waiting for the right tools and the right perspective to reveal it. And once it was revealed, it turned out to be part of something larger, something more complex, something that connected to other structures and other flows and other regions of space in ways that took years to untangle. That is how discovery works. You find one thing and it leads to another. You answer one question and it raises 10 more. You map one structure and it turns out to be part of a larger pattern that you did not even know existed. The Great Attractor is not the end of the story. It is not even the middle. It is one chapter in a story that has been unfolding for 14 billion years and will continue for trillions more. A story that includes us, for now, for this brief moment in cosmic history when humans exist and are capable of asking questions and building telescopes and measuring the motion of galaxies across hundreds of millions of light years. We are participants in that story, witnesses to a process that is vast and patient and indifferent to our presence. But we are here, and while we are here, we can look up, we can ask why. We can measure and map and calculate and theorize. We can take the scattered fragments of data, the redshifts and distances and velocities and spectra, and piece them together into a picture of the universe that makes sense. Not a complete picture, not a final picture, but a picture that is closer to the truth than the one we had before. And that effort, that process of looking and asking and figuring out, is what makes us human. It is what connects us to the cosmos, even as the cosmos ignores us. It is what gives meaning to the motion, to the fall, to the 600 km/s drift toward a place we will never reach. We are falling, but we are falling with our eyes open, and that makes all the difference. So here we are, standing on a planet orbiting a star in a galaxy that is falling through space at 600 km/s towards something we cannot see, not drifting, falling, pulled by the gravity of a structure so massive it takes tens of thousands of galaxies to build it, sitting in a region of space so obscured by dust and distance that we only discovered it by watching how it moves everything around it. The Great Attractor is not a destination. It is not a place we will ever visit or even fully see. It is a shadow, a gravitational fingerprint, a node in a web that stretches across the entire observable universe, and we are connected to it whether we like it or not. For decades, we did not know it was there. We mapped the sky, catalogued galaxies, measured distances, and assumed the universe was expanding smoothly in all directions. Then the data said otherwise. Galaxies were moving wrong, too fast, too coordinated, all drifting in the same direction like leaves caught in a current we could not see. It took infrared telescopes and radio surveys and decades of painstaking work to punch through the zone of avoidance and reveal what was hiding behind it. A concentration of mass, a pile-up of clusters and dark matter. A place where the cosmic web converges and everything within hundreds of millions of light years falls toward the center. We are part of that fall, have been for billions of years, will be for billions more. And the strangest part is that we will never arrive. The expansion of the universe will see to that. Dark energy will stretch the distance faster than we can close it. The structure will dissolve. The flow will reverse. The Great Attractor will fade into the expanding void, and the journey we are on will end not in arrival, but in dispersal. We are falling toward a place that will not be there when we reach it, and somehow that makes the motion more profound, not less. Because the universe does not care about destinations, it cares about forces and masses and the geometry of space. And those forces have set us on a path we cannot escape, toward a place we will never reach, at a speed we cannot feel, across a distance we cannot comprehend. We are passengers in a current we did not choose, witnesses to a process that was running long before we existed and will continue long after we are gone. The Great Attractor is pulling, we are falling. And the fact that the journey has no endpoint does not make it any less real. It just